Bonjour and welcome to our webinar. My name is Gunnar Keppel and I will be facilitating the webinar. I'm usually based at the University of South Australia in Adelaide, Australia, but I'm currently on a MAK'IT fellowship through the University of Montpellier and based AMAP lab. Before we start, I should also mention that this webinar was co-organized by myself, Thomas Ibanez, who's showing on the picture, and the MAK'IT team, and you'll hear more from them a short while. So why am I facilitating this webinar? So the project as part of my fellowship looks at the impact that cyclones are having on trees. And so it looks at the impact, but particularly in the context of cyclones changing as a result of climate change, oceans becoming warmer, cyclones becoming stronger, occurring in places where they didn't before, and looking then at the impact that cyclones are having on trees, on forests, and trying to put everything together in some models to predict what those changes might mean for the future and then develop guidelines and policy recommendations. And that relates really well to today's webinar. So first, we'll have Swen and Jullien talk about cyclones and how they may be changing in future. Then we'll have Thierry Fourcaud, who will be presenting on the biomechanics of trees in relation to wind resistance. Then we'll be looking at the impact of cyclones, and Kana Kamimura will be looking at impacts on forestry. Eduardo Somarriba impacts agroforestry, and Webb will be looking at impacts in natural forests. In the context of putting everything together and modeling cyclones, there is a new R package that we have developed recently, and Thomas Ibanez presenting on that. And all the presenters will also mention how their work relates to impacts on policy and potentially livelihoods. And I will use that as a theme to draw all 6 talks together in our final discussion. So that brings us to the schedule for today. And without much further ado, I will now hand over to Thierry from MAK'IT, talk a little bit about the MAK'IT program and the MAK'IT fellowship. I understand they will be opening soon again, and it's an excellent program.
Thank you, Gunnar. Good morning, everyone. I'm very pleased to be here today. I will take just a few minutes to very quickly introduce MAK'IT, the Advanced Knowledge Institute on Transition, which belongs to the University of Montpellier and is located in Montpellier in the south of France. MAK'IT was created in 2019 and it belongs to the network of Institute of Advanced Studies here in France. One of our main activities is to host international researchers from all over the world here in Montpellier and support the collaborative work with the local scientific community. We do this through 4 different programs, which you will find more information about on our website, including our Visiting Scientist program, which currently is hosting Gunnar Keppel. MAK'IT is different from other advanced studies institutes. Many of you may be familiar with the activities that are carried on in this kind of institute, but we are different in several ways. First, our mission and our vision are focused on the Sustainable Development Agenda, the 2030 Agenda, and we work on the Sustainable Development Goals of SDG. So the research project we support work with this SDG in different ways, especially with topics related with agriculture, with environment, as Gunnar, and with health. Second, we have a strong focus on interdisciplinarity. So we not only support researchers from social and human sciences as many other advanced studies institutes do, but we also support researchers from natural and fundamental sciences. Again, Gunnar is one example who is working on research on cyclones. The third characteristic is that we promote a dialogue between scientists, decision makers, and society actors. So emphasizing in this way the importance of transdisciplinarity and emphasizing the importance of interaction in the interface science, society, and decision making. Fourth, especially at this interface, we try to promote understanding between different stakeholders by inviting them to work together on analyzing controversies around different topics. This can be social scientific controversies, socio-technical controversies, but we implement this controversy analysis as a starting point for building bridges and promoting actions that support transition towards sustainability. Finally, our first characteristic is our goal of equitable representation of the Global South in each of our programs. This means that for every call, for every program we are hosting, we pay attention to have a equal representation of researchers from the Global South and the Global North. I invite you to visit our website. You can check there the different programs and also the calendars of our calls. And without further delay, I give the floor to Gunnar to start with this international conference. Thank you very much and enjoy your time today. Thank you.
Thank you very much for that quick introduction, Sarah. I would like to add that so far my MAK'IT fellowship has been an amazing experience, and the support that you would receive during the fellowship is really good. Montpellier has a great scientific ecosystem, especially for, in my field, ecology and the natural science, but in many other sciences. And the MAK'IT program, I find it particularly useful for multidisciplinary and transitional research. So I can highly recommend the MAK'IT program and their fellowships. I will try to stick to schedule as much as possible. So just a quick reminder of the program before I introduce our first speaker. So we'll have Swen Jullien talking about the climatic aspects of cyclones, Thierry Fourcaud talking about the biomechanics of tree resistance to wind, Kana Kamimura about the impact of cyclones on forestry plantation trees in forestry plantations. Eduardo Somarriba will be sharing some of his deep knowledge on the adaptations in the agroforestry sector to cyclones. Webb will then look at the impacts of cyclones on a particular natural forest before Thomas Ibanez will introduce the Storm R package, which allows calculating cyclone impact at any time, anywhere, basically. And then we will have a discussion focused around the implications of all of that research towards livelihoods and especially policy. So our first speaker then will be Swen Jullien from the Physical and Spatial Oceanography Laboratory. And she is fast becoming one of the leading climate systems and coastal system modelers. And one of the key foci of her research has been tropical cyclones. So we are very lucky to have scientist of her caliber starting off our webinar today. So I'd invite you to start sharing your presentation, Swen, and we're very much looking forward.
Okay, thank you. Is it running well?
Yes.
Okay, perfect. Thank you very much for the introduction. So yeah, I'm Swen Jullien. I'm a researcher in physical oceanography, in atmospheric and ocean dynamics at the Laboratory of Physical Oceanography and Remote Sensing in Brest. And so today I will give you an overview of tropical cyclone dynamics, their relation to climate variability and the uncertainties that we have. So the idea is just to give you some insight on the physical side, let's say, of a tropical cyclone. So tropical cyclones are known for their devastating impact on coastal areas, obviously, but they generally spend most of the life cycle over open ocean, and they just cause massive damages when approaching the coast due to their wide spatial extent and the compound effect of extreme winds, rainfall, and waves. So I have a few pictures of impact that can arise due to these extreme events. And I will first start with a few numbers to give you an overview of these giant extreme energetic machines that are tropical cyclones. So tropical cyclones can dissipate in 1 hour the equivalent of 100 to 200 times the daily energy consumption in France. So it's huge. Due to these strong energetic and extreme events, they can have a lot of human casualties and economic losses associated to tropical cyclones when they touch the coast. If we go towards some numbers on their physical structure, so these giant events are about 1,000 kilometers in diameter. On the right-hand picture, you have a satellite image of these cloudy spiraling bands of a tropical cyclone to the island of New Caledonia, and you can see the scale of the event compared to the scale of the island. They also encompass the whole troposphere, so they are 15 kilometers high, and they have very strong wind that can go up to 300 kilometers per hour. They also strongly impact the ocean underneath them. They can generate waves that can reach up on even a little more than 50 meters high, and they have a strong impact on the whole ocean structure down to more than 500 meters. And this response is usually a lot seen from the surface of the ocean, and they can go to up to a 10-degree cooling in the surface. And I will come back to that a bit later. So these giant machines, where and how do they form? So they form in tropical areas. Why? Because actually they are fueling from the evaporation of the ocean surface. So they need warm ocean. So this is the case in tropical basins. And we can see that they can have different names in the different basins, so hurricanes or typhoon or just tropical cyclones, but all refer to the same phenomenon. And we can also see that over the globe, there are some areas where we don't have tropical cyclone, and this is due to unfavorable environmental conditions. And over the year, it's about 90 tropical cyclones that we can have, but this number can vary from 1 year to another. So basically, they form in what we call the intertropical convergence zone, which are convergence zones in tropical basins, and they don't form in non-convective area, and this is the case of, for example, of the southeastern Pacific, where we don't have tropical cyclones, and they also don't form in areas where we have intense wind shear over the vertical, and this is, for example, the case of the South Atlantic. That's why we don't have tropical cyclone in these areas. Once they are generated, this tropical cyclone intensify up to what we call a mature stage in about several hours to several days. And finally, they propagate advected by the mean tropospheric flow. So first, generally westward under the effect of easterlies, and then gradually shifting polarward due to the planetary vorticity. Finally, they end their life in possibly different ways. So they can make landfall, and making landfall, they lose their ocean evaporation fuel, so they die. but their size can have a strong impact at the coast before they die. Or they can also reach some areas where the environment is less favorable, that is with more vertical wind shear or a colder ocean, and this is the case when they reach the subtropics in general. And typically, this whole life cycle is about a week. So we know some stuff about tropical cyclones, but we have also strong uncertainties on them. And as said by Thierry Manuel, that he's a researcher on tropical cyclones for now decades, there are no aspects that are as proved as more vexing than tropical cyclone genesis. Indeed, at every time step, we have various numerous cloud systems in the tropics, as illustrated on this satellite picture, but not all of them become tropical cyclones. And so we know several necessary conditions for their formation and catalytic processes that favor their formation, like easterly waves or monsoon through, but not sufficient processes. So we know that we need a warm ocean surface, we need sufficient relative humidity at mid-troposphere, we need some conditional instability, some vortices or pre-existing vortices in the low level, and a weak vertical wind shear. But even if all these conditions are gathered together, sometimes tropical cyclones do not intensify and generate, actually. And so we have, in the research community around tropical cyclones, various scenarios that have tried to explain the appearance of this warm core, deep convection that is the tropical cyclones. And so trying to explain how we start from what we have on the picture on the bottom, these little spots of convection that can actually gather to form eventually a tropical cyclones. But this is still a matter of research, so we still have a question on these processes of formation and still uncertainty on our ability to forecast this genesis of tropical cyclones. So now just a few words on how the intensity of tropical cyclone is modulated, because I think it's a quite important point. And first, I will start by introducing these two plots that are actually the evolution over the years from the 90s to about now of the error that we have on the left, the forecasted track of tropical cyclone, and on the right, the forecasted intensity. And we can definitely see that we have strongly improved our ability to forecast track. So we are now clearly better in forecasting track, but our ability to forecast intensity has not improved that much. And this is due to the fact that it's quite difficult to forecast tropical cyclone intensity, and we still have improvement in our understanding to do, notably on the three topics that I have written there. So this is processes that arise in what we call the boundary layer, so the layer that is above the ocean surface. The fact that we have strong ocean atmosphere interaction in these systems, and it's very difficult to observe this interaction and thus to improve the modeling of this interaction. And also the tropical cyclone is a giant machine with very various scale interaction, and this is something very difficult to model. If here I represent the tropical cyclone on this vertical section, so on the right-hand side, so you have the ocean underneath, then what we call the boundary layer, which is about 500 meters to a kilometer above the ocean, and these different spiraling bands of clouds separated by dry air intrusion, where we have subsidence in the dry air intrusion. And overall, the circulation in this horizontal vertical plane is what is pictured with the red arrows. So we have convection in the region that we call the eye wall, and we have low-level convergence on the bottom and a divergence in the upper levels. And how is the tropical cyclone intensifies? So once we have deep convection, so this horizontal verticulation that is initiated in the eye wall, due to the ascent of air parcels, there release some heat from the eye wall to the environment, and this has the effect to increase the cyclonic winds above the boundary layer. And this increase of cyclonic winds will increase the low-level convergence, and so will increase the convection. And the convection will increase the tangential wind. So there is a positive feedback loop between the convection and the tangential wind, so the wind circulating around the tropical cyclone, that's made this machine self-sustaining. So we have, once initiated, the tropical cyclone can intensify by itself. Obviously, it's limited by the amount of energy that is available, which is stored in the ocean. So it's modulated by the available ocean heat content underneath the region that tropical cyclones pass over. And this extreme event then have a strong impact and feedback to the ocean. So they generate high waves, as I said, but also a very strong oceanic response as the winds tend to mix strongly the ocean, and the cyclonic circulation of the wind tends to do so what we call Ekman pumping, which is an upwelling of the water due to the cyclonic rotation. So basically, with mixing and upwelling, we are bringing cold waters toward the surface, and so we are strongly cooling the surface, and this have an impact on the evaporation. So it limits the evaporation and thus limits the tropical cyclone intensity. So we have to account for this very strong feedback in tropical cyclones to understand their life cycle and their evolution in the future. And basically, this ocean response also have other implications. So as we upwell waters from the subsurface of the ocean, we also bring nutrients towards the aquatic layer. And so we can have phytoplanktonic bloom in the wake of tropical cyclones, for instance. And we also store some heat due to the mixing under tropical cyclones towards the subsurface of the ocean. So we bring cold water to the surface and warm water in the subsurface, and this can have impact on the climate system, as this warm water can be advected somewhere else and then released back to the atmosphere at some different places. So this is why this actually sporadic event that are tropical cyclones can have a strong impact on the climate system. Now, if we go towards interactions with the environment, other interaction can be within the atmosphere. So if the vortex encounter an area where there are strong vertical wind shear, so a difference in the wind between the surface and the upper layers, it will tilt the vortex. And it's a perturbation to the vortex that will lead to a reaction of the vortex, let's say. So if we look at this view, top view of the tropical cyclone that I've put on the bottom left now, when the vortex is perturbated, it can be by cooling from the ocean or tilting by vertical wind shear, for example, it will respond and try to recalibrate. And to do that, it will emit some waves, like typically vortex Rosebery waves, or create little mesovortices about 1 kilometer size in this eye wall region, which is the most energetic of the tropical cyclones, and try to dissipate this perturbation. And so doing that, we can see that we go towards a very large-scale vortex, which is about 1,000 kilometers wide, toward processes that are really small at the scale of kilometer or even lower than that on the scale of turbulence. So to model these events and to be able to project them in the future, we have to account to a lot of processes. And here I've just put a slide to maybe introduce, maybe you're familiar with that, but I think it's something that we have to keep in mind. So to model tropical cyclones, we basically use most of the time dynamical models. So it's typically atmospheric models that can cover the entire Earth or some parts of the Earth. And in these models, we have to solve a lot of different processes. So we have to solve microphysics, radiation, interaction with the ocean, with the waves, interaction with the land. And so all these processes have to be accounted for. And obviously, as I said, we have to account for the coupling between the atmosphere and the ocean, which is essential in the case of tropical cyclones. And we also have to deal with the fact that we have some stochasticity in the Navier-Stokes equations that we are solving. And so to get an overview of what we could have, on the bottom left, you have an example of how we do in forecast. We have to do ensemble forecast to be able to deal with this uncertainty that we have in the equations. So we have to solve all these complex features that goes to basin scales towards turbulence. And so it's quite complicated. Now, if I go to the climate variability and the impact of tropical cyclones, first, I will show you on the left, so the stormy days so tropical cyclone days for the different basins as a function of season. So in black, it's a global average, and in the different colors, it's the different basins. And basically, we have tropical cyclones during the summer-autumn season in the different basins, except maybe in the North Indian Ocean, which is the curve that is with the white circle in red and white circles, where we have two peaks due to the special seasonality of these basins. And this seasonal repartition can be also slightly different from one year to another due to subseasonal variability or large-scale variability. On the right-hand side, you have a map of the correlation between observed cyclogenesis and the El Niño 3.4 index. And this El Niño 3.4 index is an index representing some interannual variability associated to the El Niño Southern Oscillation phenomenon that arises in the Pacific basins mainly, and which has a tendency to change large-scale conditions for tropical cyclone genesis. And typically, for example, when we are in El Niño years, so under El Niño conditions, we have a weakening of easterlies, and this weakening of easterlies can let the tropical convergence zone go more eastward, and that's why we have an increase in tropical cyclone genesis in the Central Pacific in these years. While during El Niño years, we have an increase of easterlies, and so the cyclogenesis is more confined towards the western part of the basin. So when projecting tropical cyclone activity and forecasting it, we have to account for this climate variation of the large-scale synoptic features that led to a change in the convergence zone location and thus to the genesis of tropical cyclones. Now let's go to climate projection. So here is a map from the IPCC report, and you can see on the bottom the global trends of tropical cyclone change under a 2-degree global warming. And you can see that the average is that we should have a decrease in frequency, an increase in intensity and in the rain rate in tropical cyclones. But you can see also that we have strong error bars. So sometimes we don't know if the change is positive or negative. And we can also see that these global trends can have very strong regional variation. And if we look at all the panels in the different regional area, we can have very different trends. And what is important to remember is we have these trends, okay, but we have strong uncertainty around these trends. And I will try to explain a bit why we have such uncertainties. So first, climate models have strong biases. Here on this picture, you have the multimodal mean from all the IPCC models, the mean of precipitation and sea surface temperature. And on the right, you have the bias of precipitation and sea surface temperature in the present day climate. And you can see that typically these biases are quite high in the region, the tropical convergence zone area, so region where we have tropical cyclones. And because of that, it's difficult to have robust projection because even at the present day, we have some biases. So we need to first correct the biases to have more robust projection of how cyclone can evolve. Then we have another strong issue in tropical cyclone modeling in climate models is due to resolution. So typically, a climate model is about 1 degree resolution, sometimes half a degree. But basically here you have an illustration of a tropical cyclone rain precipitation field modeled in a 1 kilometer model, in an 8 kilometer model, and in an 80 kilometer model, which is typically climate models. And you can see that definitely the pattern is not really realistic in the climate model. And basically, tropical cyclones are generally weaker and too large in climate models. On the right-hand side, you have a distribution of tropical cyclone days as a function of their maximum wind speeds. And in black, it's from the observations, so the present day observations. And in blue, it's the curve for a climate model in the present day. And you can see that in a climate model, we cannot model very strong tropical cyclones. It's not possible due to this issue in resolution. So we have to draw some trends between future and present based on the blue and red curves. And we can draw some trends, but basically it's very difficult to know what will happen to very strong tropical cyclone in such models. So to circumvent this issue that we have in climate modeling, we still have tools, of course. And for example, we use what we call indices of cyclogenesis or maximum potential intensity that are based actually on large-scale variables. So large-scale sea surface temperature, vertical wind shear, planet vorticity, synoptic flow, and stuff like that. And so here we are more confident on what we're looking at compared to really small-scale features such as directly tropical cyclones. And from that, we can draw some trends on how the tropical cyclone will evolve. But this requests, however, to correct the biases, even in these large-scale variables that we can have in climate models. Another way that we can use to model tropical cyclone in the future is what we call regional downscaling. So this is what is pictured on the bottom. The idea is to increase the resolution of the model locally and to force the model at the boundaries with climate model data. So this is a way to better represent tropical cyclones. But once again here, we have to get rid of the biases of the global model first. Now I will just finish with another tool that we have and that Thomas will also introduce a bit later. It's the use of simplified tropical cyclone models or empirical approximation of the wind field that we use for climate projection, so to represent climate eventually in the future, also vulnerability issues, typically storm surge, ocean waves modeling, or even ecology. And the idea of these models is actually to represent the cyclonic wind field in the simplest way. So basically on the right side, you have different profiles, intensity profiles as a function of the radius of the tropical cyclone. So on the left, we have the eye, and on the right, we have the outer core region. And we can see different parameterizations exist in the literature. So you can see that we have different possible parameterization. And this is interesting, but also there are quite smooth, obviously, because it's an average and it's a simplified representation. But it is very useful, and it can be used to create a wind forcing based on a few number of parameters, such as, for example, the maximum intensity and the size of the storm, so the radius of maximum winds. And basically, this can be used on existing tracks, so that are provided, for example, by the best track data, which are the track that we have from Forecast and Analysis Center on tropical cyclones, or even on the bottom on synthetic tracks. So the idea is there, for example, in the Bay of Bengal, in this publication, we have a few tropical cyclones, and it's difficult to know how the impact could be if the tropical cyclones was just a bit on the left, on the right-hand side when it arrived at the coast. And so we can generate synthetic tracks, and also we can generate synthetic tracks for future conditions, large-scale conditions, and apply this kind of models on these synthetic tracks to get an idea of how the tropical cyclone could impact the ocean or the coast, for example, under these conditions. So now just to summarize, what do we know and what do we still miss in the tropical cyclone research area? So for genesis, we know necessary condition, but not sufficient. And we still have research on the scenario leading to deep convection in tropical cyclones. Regarding the intensification, we know that this machine is self-sustained, but we also have several candidate mechanisms. And there is still debate in the community to know if the spin-up of the tropical cyclone intensification is more associated to what's happened above the boundary layer or inside the boundary layer. And this is due to the fact that it's very difficult to observe tropical cyclones, and especially the boundary layer, which is underneath all these clouds and all this rain, and this is difficult to observe from in situ data. Obviously, it's almost impossible, and from satellite, it's not that easy. Regarding the variation of intensity, which is kind of a strong challenge in forecast, because we now have sometimes rapid intensification that can cause a lot of damages. We know that they are related to various things, but it's very difficult to account for all the things in models because it's very complex. So with the impact of the large-scale flow, the ocean interaction, and the interaction between the scales of the tropical cyclones. Regarding the climate variability, so we have seasonal and interannual variability associated to the climate mode of variability of the different basins. And this is something to account, obviously, for seasonal forecast, for example, but we also have stochasticity. So, and this is very dependent on the basin that we are looking at. For example, the South Pacific is typically a basin where we have strong stochasticity. And this is, for example, less the case in the North Atlantic basin. Regarding climate projection, we have trends, but we still have very strong uncertainties. And due to the coarse resolution and the biases of the climate models, we have to rely on indices or to rely on bias correction and specific downscaling to have more robust projection. And I will just finish with this picture. It's a picture of actually satellite acquisition with a RadarSat constellation over the tropical cyclone Freddy that was an exceptionally long tropical cyclone in the Indian Ocean that arose recently. And we can see that now we can have sometimes good sampling of the tropical cyclones, but it's not a continuous sampling. And we have actually very few images of this quality with very high resolution representation of the wind field, thanks to satellite data, because we don't have satellite data all the time. And this is something that we still have to push forward to the policymaker to keep increasing our capacity of observation, because we definitely need that to improve our understanding and capacity of modeling of these tropical cyclones. Thank you.
Thank you very much, Swen. That was a beautiful introduction to cyclones, and thank you very much for that. If you have any questions, as Sarah mentioned, if you could post them through the online chat. In the meantime, so you gave a really good overview of all the uncertainties involved with cyclone modeling. So if you had to give an advice to policymakers in governments that are in cyclone areas for the future, what would it be? Or would it just be, well, there are too many uncertainties to say much?
It's a difficult question, of course. Basically, no, I think we have uncertainties, but we have tools to improve, to limit these uncertainties at time. So definitely we need more observation, because we are constrained by the fact that we have many theories and scenarios now. So we have theorized a lot what happens in tropical cyclones, but we need observational evidence of them, and especially what happens in the boundary layer and in interaction with the ocean is something that we have to get more data to be sure of what we have theorized, and what we could put in numerical models to improve our forecast and our projection. So this is the first point. I think it's quite important, and also we have to keep going towards improved projection. So improved projection means definitely improved models first. So we can go towards increased resolution, or I think that's globally it will be very difficult to go there because it's a lot of numerical hours of computation. But regionally we can do some stuff. But we need to correct the biases of the global model. So we have some tools to do that, statistical correction and stuff like that, but we still have to improve this correction. And this goes with just the general improvement also of climate models. So I think, yeah, we have to keep going on the track that we have started to improve climate projection in general, to be able to have better estimation of tropical cyclones. And I just wanted to make the point that we have strong uncertainties, and we don't have to say, we have to keep in mind these uncertainties when saying things about tropical cyclones future impacts.
Thank you very much for that, Swen. And is there any other question? So we're almost, well, we're basically at the time for our next speaker to start soon. Is there any urgent question? I haven't seen. There's one from Thomas Ibanez, and he asked, what are your thoughts about observed and predicted poleward migration of cyclones? Because, yeah, there's a bit of literature suggesting that cyclones may be moving slightly further north and south, affecting new areas.
Yeah, actually, it's really dependent on the basins first. And there were a lot of studies of that in the North Atlantic, because it's a basin where we have a lot of research because it's close to the US, and definitely they have some means to do more research there, I guess. But it's actually a complicated question, because it relies on the fact that sea surface, on both things. The sea surface temperature increase, obviously, so we have more energy available for tropical cyclones, but we have also the shear, so the wind shear, that is a strong constraint on tropical cyclone evolution. And what I was saying is that as we have strong uncertainties on the pattern of sea surface temperature and vertical wind shear, it's also difficult to draw conclusions. So I think in the North Atlantic, maybe there are less uncertainties, and we have indeed observational evidence in the recent years of some trends. This modulated by the interannual variability, of course, but in other basins, it's not necessarily the case. So it will really depend on the basins and the re-equilibration, let's say, of the climate system in this change in the sea surface temperature gradients, for example, and the movement of the convergent zone that we can have.
Thank you very much for that, Swen. And thank you very much again for a very exciting presentation. Jullien, I think we... yeah, so Swen, if you, I'll ask that last question, if you could stop your share, and if Thierry,
Yes.
if you could start putting your slides up. And sorry, do you have that question? Oh, there it is, sorry. So Jullien was asking, could you elaborate on changes in seasonality for cyclones associated with climate change?
Yeah, I cannot, I would say, just like that, because it would request to go into really basin variability, because typically seasonality is very different depending on the basin. So I think we can have several answers to that. It depends on the basin and the various studies that we can have on that, but it really depends on how the climate system is reorganizing with that. But yeah, sorry for not a more precise answer, but it's very difficult to answer that regarding the variability of factor that we have in different basins.
Thank you very much, Swen. Thierry.
Yes,
So,
good morning.
Good morning. So our next presenter then will be Thierry Fourcaud. He's the director of the Joint Research Unit on Plant Architecture, Functioning and Evolution, AMAP, and he's a leading specialist on tree biomechanics in relation to wind. And I know there would be very few of us in the audience who would not have read one of his outstanding influential publications in that field. So without further ado, I'll hand over to you, Thierry. And
thank you very much, Gunnar. I don't know if you can see my presentation or not. I don't see anything on the screen, but try to. So I have a lot of technical problems this morning. I don't know why, but so I try to. Okay, so this is not this screen. This is this one. Not sure it's going to work.
Okay, there is, yes, there's some orange, red background.
Yes, I don't know why you see an orange thing, because I have two screens, so this is very difficult to manage. Maybe you should be ready to, yes, maybe you have got my presentation, I guess. So it's maybe
let me do that really quickly,
because I am afraid it's going to be complicated. If you can.
Yes. Okay.
So I have to stop sharing.
Okay. Yes. So I will put up the slide. And just let me know when to move on to the next slide.
Okay, I will tell you. Thank you very much. Okay, so good morning, everybody. Thank you very much to the organizers to give me the opportunity to present this topic, biomechanics of trees in relation to wind. You can go next. Okay, so this is a plan of my presentation. Most of my talk will be related to the concept of tree biomechanics, but concerning short-term wind loadings, because this is a topic today. When I'm talking about short-term, I mean a few seconds to a few minutes. And that means also that tree structure is not considered here as a growing structure, but given at a developmental stage. So in the second part, I will quickly introduce the notion of thigmomorphogenesis and acclimation of trees to wind or gravity. And of course, these processes are integrated during a longer term period. And also for each section, I will talk about first crown-wind interactions, and secondly about root soil interactions. That is very important from the tree wind firmness point of view. So you can go next. So when we consider short-term period of time, we have we can use what we call a civil engineering approach that is quite classical in to calculate or to estimate the ability of engineering structures to resist forces in general or loadings. So you can go next. And first, don't be afraid. I will not give you a lot of equations or even no equations, but you have to know some basic concepts I use in during my talk. So I try to explain for people who are not expert in mechanics. So first, a tree is a structure that is built with slender structures that we used to call beams. So this is an important beam theory is an important topic or to address the question of tree stability. So what is a beam? The beam is a slender structure. That means that the length of the beam is much larger than the diameter of the beam. And also another concept is the concept of beam stiffness or bending stiffness of a beam. What does it mean? It means the resistance, the stiffness is the resistance of the beam against bending deformation. So you can see here in these pictures that the stiffness depends both from material properties, that I will explain you later, and also from the beam dimensions, and in particular, the beam diameter or radius. So on the left, you can see that a small beam, with a small radius, is much prone to bend than a beam with a big diameter that you can see on the right side of the picture. This is also exactly the same if you consider a beam with the same diameter. If you decrease the modulus of elasticity, that is a material property, you will increase the deformation of the beam. So you can go next. Next, please. Oh, okay, that's okay. It's okay. Sorry. Another important physical quantity is what we call the stresses, the stress field. What is a stress in mechanics? The stress is internal, something to measure the internal force within the material. Is usually a force divided by a surface and expressed in Newton per meter square. So stresses are important quantity that is usually considered to understand or to evaluate if the material can resist or if the structure can resist a certain level of loading. So this is the quantity we are looking at to see if there is a risk of failure or not. So, of course, the risk of failure is defined by a kind of by what we call a stress threshold called modulus of rupture. So this is the maximum stress that the material can withstand. So this is a very important parameter. And in terms of forces, of course, we can apply a force at the top of a beam here. And this force will be transmitted to the base of the beam. This beam is perfectly encastrated in the soil. And there is another important physical quantity that we call moment of the force F, that is given by multiplying the height of the lever arm. So this means the distance between the point of application of the force and the point where we consider the moment of the force. So this is also a very important quantity given by the product between the height h and the force F. To finish, we have another important geometrical quantity that is called the second moment of area. And you have just to consider that this quantity is calculated or is proportional to the radius at the power 4. This is very important because this means that these geometrical parameters have a very significant weight when we consider the risk of failure of such a structure. And so you can see here on the right also that according to the formula of the moment of area, we can observe that the maximum stress at a given cross-section area, so the maximum stress is at the periphery of the stem. The maximum stress is negative in compression windward and is in tension, so positive leeward. And this maximum value is equal to 0 at the point of the force application and is maximum at the very base of the beam when the beam is cylindrical. So you can go next. So of course here a tree is not a perfect beam. A tree is a genius, stable structure. With a design, what we could say that the design of a tree is optimized with regards to to resist external loadings as gravity or wind forces. When a wind is applied to tree structures, this wind in fact, exerts, of course, what we call a drag force. A drag force that is mainly applied at the crown level where the leaves are present, and these forces are translated to the wall structure into a bending of the stem. So the mechanical stresses here are, as usual, in tension at the windward side of the stem and in compression at leeward side of the stem, as I said before. And of course, most of the forces are also transmitted to the soil plate compartment. That is also very important to consider with regards to tree stability. So this compartment, I will talk about this a little bit, but this compartment is very complex, and the resistance of the root soil plate depends on several factors, as, for instance, root architecture, soil physical properties, or etc., etc. So when we look at the tree stability, we have to consider all these different compartments, all these different processes, in order to estimate and quantify the risk of failure. You can go next. So, of course, the material building these particular structures is called wood. Everybody knows that. And the wood is a very complex material with, as a first, this is an orthotropic material. That means that the mechanical properties are different in the different directions. So the directions are not represented here, but by directions, I mean the longitudinal direction, so the direction along the length of the stem or the length of the fibers. And there are two other dimensions, the radial dimension and the tangential dimensions. So usually when we consider tree bending, we consider more the longitudinal components of the stresses, deformations, and so on. So I will talk, when I talk about stresses, from now I will talk about longitudinal stresses. So in the direction of the stem axis. So there are two important components here. I have talked about this already, that are the modulus of elasticity, so the ability of the stem to deform, and the modulus of rupture, so the ability of the stem to resist breakage. And these two important properties are highly connected or correlated to the wood density. So wood density is a property that is usually used in the topic of tree stability, and I know you use this concept of wood density very often, but the reason why it is important in terms of tree stability is because it is correlated to these two important quantities. So you can go next. Here you can see, the message here is to I want to insist on the fact that the wood properties are not constant within the tree, are not homogeneous. So there is a huge variability of these wood properties. For instance, you can see on the left the variation of the wood density and thus the modulus of rupture and modulus of elasticity when you look from the center of the stem, so from the piece to the bark. So you can see these very particular shapes that are usually encountered in trees. So it's 99% of the trees can we can observe this kind of curves. So you have two different parts. One part when where the wood density is increasing, and another that is called the juvenile wood zone, and another part where the wood density is more constant. And this part, we call this part adult wood. And if you look from the base to the top, you can observe that at the top of the tree, you don't have adult wood. So it is admitted that the juvenile wood is formed when the within the tree crown, and the adult wood is formed below, above below the tree crown. Sorry, below the tree crown. Another important thing you can see on this slide also is that the maximum stress profile is very different from a cylindrical beam. Here, this is due to the particular shape of the evolution of the diameter along the tree stem. And you see here that the maximum stress is not at the base of the stem, but above this, above the soil. So this is also very important, and maybe because why the reason why you can observe that the tree breakage are never occurring at the very base of the stem, but more at 1 or 1.5 meters. So next. Okay, so I show here a first study that has been carried out with my colleagues in Grenoble, Benoît Courbeau and Philippe Ancelin. This work considered the tree structure as a very simple structure with a simple crown shape and a stem, slender stem. This study was based on the calculation of the stresses within the stem, considering 2 types of data. So data coming from real trees measured on the field, and other data coming from simulations or forest growth simulations. So you can see here the distribution of the variability of tree diameters, but this is the same, of course, with the tree height. And we made the simulation on this set of trees, and this the curve here shown the wind damage amount of failure when the wind speed increases. So of course, when the wind is very weak, you don't have broken trees, and when the wind accelerated, you have more and more trees broken or uprooted. So you can go next. What is interesting here is to see the effect of the 3 dimensions on the type of damage we can observe. And in particular here, when we are looking at the effect of the slenderness, it is clear that youngest trees, on the left here, you have the youngest trees that are thinner and little bit with a small slenderness, are more resistant to wind and usually not damaged. In comparison to other trees that are medium trees with bigger diameter and a little bit taller, and these trees are more prone to stem breakage. And on the very right of the curves of the histograms, you can see that the biggest trees mean trees with a very large diameter, and usually smaller, relatively smaller compared to the diameter. These trees are more prone to wind throw. So this is very important to realize that the dimensions of the stem and the trees is a key point. Of course, this is the same with the dimension of the crown, because this is very important to calculate the drag forces, of course. So you can go next. Here I'm going to talk about what we call the dynamical response of a tree to turbulent winds. So this is a much more complicated processes. Next, I try to summarize here. what it means. So when the tree is submitted to wind or excited by wind provide mechanical energy. This mechanical energy is transferred between the different structural elements. So I mean the branches, the stem, the tree roots, and between different modes of deformation. And also trees are moving in terms of dynamical movements. I'm talking about dynamical movements. So trees, branches, stems are moving in the wind, and this move is usually dumped for two reasons. The first one is due to the what we call material dumping. So this is in fact linked to the material properties of the wood that is involved in the dumping of the structure. And another dumping comes from the friction of the leaves to the air. So this is what we call aerodynamic dumping. And there is a last process that is involved also in dumping. This is a dissipation of energy between the different tree structure elements. So you can go next. So we have used these, we tried to use numerical models in order to quantify these different processes, to quantify the damping of the structure according to the tree architecture, but also the distribution of stresses within the tree when the tree is submitted to turbulent winds. So here we started this study measuring real trees on the field. So we measured, of course, the wind characteristics, but also the tree movements and also the tree architecture. So you can go next. We use that to develop the numerical models. And here, I don't know, I'm not sure. Maybe if you click on the picture, you can see the tree moving. I hope it works. Yes, this is a movie. And so you can see here the simulation of the tree movement when the tree is submitted to a real wind. So the wind have been measured and used for the simulations. And the colors you can see here correspond to the distribution of stresses within the different structures. So when the color is red, this means that the stress is very high. When the color is blue, this means that the stress is very low. So you can go next. Of course, so we have used this simulation software to make a design of experiments. So we just varied first the different structural dimensions. So for instance, the length of the branches, of the stem, etc., and also the diameter. And we did the same, but varying the material properties. And the idea was to see what parameter was the most important in terms of tree dynamical response. So you can see clearly here that the most important parameters are the geometrical parameters, and in particular the ratio between the height and the diameter of the stem, but also the specific leaf area that are very important in terms of dynamic amplification factor. So these decrease this dynamic amplification factor, and also the length of the branch of what we call order 3. So these are the small branches within the crown have a very important effect on this response. And also these geometrical characteristics play a very important role also in terms of turning moments that is transmitted to the root system. So you can go next. I have forgotten to say that the material property, of course, are important, but are not the first factor we have to consider here. So next, I want to go further in the mechanics of the root anchorage. You can go next. So roots are very complex systems, very plastic systems, and you can see here a representation of different root architecture for different tree species. So you can see that the shape, the branching organization is very, very different, and also the size of the different root systems, according, of course, to the age of the tree, but also to the soil properties. You can go next. So we did some similar numerical studies, but this time considering the interaction between the root structures and the soil. So you can click, or maybe you can click on the picture again, so you can see the simulation of, no, we don't see anything maybe, but it doesn't matter. So the idea here is to do, as we did before, design of experiments varying the property of the soil. So in fact, we have two different contrasted soils, clay soil and sandy soil. And we put different root architecture within these particular soils. And we just estimated if these root systems with particular root architecture are better or less strong according to root with regards to the ability of trees to resist wind throw. So one key point here, for instance, I don't want to go very in the details, but what we can see here, for instance, is that the taproot, which is a vertical root going very deep within the ground, has a very significant effect in sandy soil, but this effect is less in clay soil. So this is just to give you an idea of what we found here. So if you go further, you can see this is another presentation of these important results. You can see here the effect of a root system where we have removed numerically the taproot. And you see here when we remove the taproot, then the strength of the root anchorage is decreased very, very significantly. So you can go next. So this is a short representation of the relative importance of different root elements. This is this example has been comes from a study carried out on maritime pine trees that grown in sandy soil. So you can see here the role of the taproot that represents 60% of the root anchorage. So you can go next. I'm going to go very quickly here because I have only 3 minutes left. But if you want to know or to know better about what I'm talking here, you can look at the publications that are. I give the references here in the following slides. So good. So in fact, a tree is not a static structure, but is a growing structure, and this is very important from the biological point of view to consider this. So why it is important? Because tree is able to adapt its shape to its environment. So you know this, it's very clear that a tree adapt its shape to in order to capture a maximum of light. But this is not the only functions of the different tree elements. And the tree must also minimize the risk of wind failure. And this happens only if the tree grown in the wind. So the tree experience the wind loads. If the tree never experience this kind of loads, of course, it will be weaker. So this is very important to know that tree acclimate to wind loading. So you can see here a classical what we call flag shape tree. And this is the result of what Jaffray in the 1973 defined as the thymomorphogenesis processes. So this is the tree is designed to adapt its shape to decrease the forces, the wind drag forces. So you can go next. This is true also when we look at the, it's more difficult, but when we look at the tree architecture, you can notice that the cross-section of the main structural roots are not circular, but usually with a specific shape here that is very performant from the mechanical point of view, and that make these roots very stiff with regards to bending. And also, if you look at the root structure itself, root architecture itself, you can see that you can notice the very big roots, so with a large diameter leeward, and more ramified structures windward. So this is also a very efficient adaptation of tree growth through improved root anchorage. So you can go next. There is also some studies published in the literature about what we call tree acclimation and growth stresses. So what I mean by reaction wood and growth stresses, that the trees, when a tree is unbalanced or lent by the wind, but it's not necessarily broken at any time, but sometimes just lent. So the tree is able to generate internal forces in order to release or to straightening up. So this is like muscles, I would say. So this is due to the specific reaction wood fibers that are shortening or elongating on one side of the stem, and this deformation of the wood cells generates forces that bend the tree. So this is an active reaction of the tree. It's a very long-term processes that are not visible. It takes a long time for the tree to become straight and vertical, to recover its verticality. But this is something very important because these processes generate a high level of internal stresses that are also responsible, for instance, of tree cracks when you cut, when you saw a tree. So this release of growth stresses has an important effect on this. And also these internal stresses has also an effect to increase the resistance of trees to the resistance of trees with regards to wind throw. So I don't want to explain this. I have no time. So you can go to the last slide. So I put here the take-home messages. So of course, the previous studies I was talking about were carried out on healthy trees. So this is an important also factor, that if the tree is not healthy, of course, is more prone to breakage or wind throw. So also another message is that wood density is an important proxy we are looking on in order to measure or to quantify the resistance of or the wood strength within the stem in particular, but also the roots. The stem diameter is also one of the first factors explaining the resistance of the stem. And tree diameter, of course, depends on tree age, but not only. This is also a factor that can vary because of the secondary growth rate. So a tree can grow very quickly and make a big tree with a less dense wood properties, but this is very important from the mechanical point of view, to have a large diameter. And the constructor is also involved in to calculate the drag forces, but also involved in the movement of the tree and the damping of the tree response to turbulent winds. The root anchorage is also hugely dependent on root soil interactions, and that root structures or root architectures can be adapted to specific soil types. And also that tree acclimation to wind is a significant factor we have to consider when we're studying tree resistance to wind. And this training of tree to resist the wind is crucial in this from this point of view. And at the end, that growth stresses are also something very often neglected, but that should be taken into consideration if we want to understand better why big trees resist gravity and strong wind forces. So thank you very much. I'm very sorry because this is I tried to give in 30 minutes a lot of information, and I hope you are not lost with this long talk.
Thank you very much, Thierry, for amazing presentation and overview into tree mechanics. And I know that anyone in the audience working on plant functional traits and wind effect on trees has a lot to think about now. I'm sorry we do not have times for question now. Maybe towards the end, after all presenters are finished, if you have any questions for Thierry, if you could send those through. If not, contact him directly. We now have to move on to, well, we now get to move on to Associate Professor Kana Kamimura, who works in the Department of Agriculture and Life Sciences in Shinshu University. She is an expert on wind damage in forest management. She has many years of experience in studying wind damage in trees with an eye on forest management, as attested by many very well-cited publications. So I hand over to you, Kana, if you like.
Okay, can I share my screen now? Is that okay?
Perfect. Thank you.
Okay. So thank you for introducing me. Hi, everyone. First, I want to thank Gunnar and Thomas for giving me such a great opportunity. So now I talk about our research project about how trees respond to strong wind by tropical cyclone. So first, I will quickly explain the background of our research and how it connects to forestry activity. Second, I will show some results from the paper we published last year. Finally, I would like to show what we can contribute to forest owners, forest managers, and policymakers with academic research. So already Swen explained a lot about tropical cyclones, so I don't need to say much more about that. But as you can see here, there are several names of tropical cyclone, and typhoon is regional name in Northwestern Pacific Basin, I think. And I'm living here now, so it's a small house. And as you can see here, some countries have faced frequent typhoons, a tropical cyclone. Also, many regions near the equator often have rich forests. So, which means enormous forests have been threatened by strong winds from tropical cyclone. So, generally, the trees growing in strong wind environment acclimate to such severe conditions. So Thierry already said that. And however, climate change is warming seawater, letting tropical cyclones migrate further north in the northern hemisphere, so further south in the southern hemisphere, and become stronger and bigger. So these figures, it actually show if tropical cyclones migrate further north, many unacclimated forests may be suffered from strong winds much more intensively than ever before. So what can we do to reduce forest damage risk under climate change? We can't change the routes and sizes of tropical cyclone, but from the previous studies, changing forest management can improve the stability of forests. I am a forestry researcher and try to find basic idea of tree failure by strong winds, coupling with weather conditions like tropical cyclone. To date, there are several usable models to help make forest management strategies. My current focus is to provide information and also additional parameters to improve such models, because models, GIS, database are also communication tools to encourage stakeholders to understand their forest conditions and options. And also, I'm simply curious why some trees fail and others do not. So now what we know and what we don't know. There is a question. We know the forest conditions before the damage. We simply go to the forest and measure trees, or use a drone or satellite image, etc. And we know forest conditions after the damage. Again, we simply go to the forest to check the damage. The problem is we do not know what's happening when the huge typhoon comes. It is very dangerous to enter a forest during the strong wind. We can't make an exact prediction of damage to set sensors in advance. We can't use satellite image because of the huge cloud. A drone is useless in a strong wind. Maybe we need small robots, but not available now. Maybe yes, but not for forestry right now. So instead, many researchers try to estimate such dynamic tree behavior based on some techniques such as tree pruning experiments and tree swaying observations in forest, wind tunnel experiments, and computer simulation. But none of them have been fully evaluated due to the lack of dynamic data from failed trees. So now I am conducting some tree swaying observations. So I will show what we have found in the following slides. So I said in recent years, I focused on tree dynamic behavior based on tree swaying observations in two projects. The project one from 2017 to 2019 is for understanding how multiple trees sway together. Project 2 from 2020 to 2023 this year is for understanding how a whole tree responds to wind. A whole tree means a stem, roots, and soil around the tree. In the middle of the first project, 2018, we actually accidentally succeeded to get tree sway data from the damaged trees by a super typhoon and published a paper last year. I will present some result. It is an open access journal, so anybody can freely read this paper and download the data which we got. So let me briefly explain the research plot. The subject tree species is Cryptomeria japonica. The common name is Japanese cedar, which is the most popular commercial conifer in Japan. We used genetically similar trees, which were siblings, so having the same parents. And 2-year nothing trees were planted in 2005. So they were not so old when the typhoon came. In 2017, we set 2 research plots in the experimental forest owned by Research Institute in Japan. And I totally forgot to put information about the tree. So DBH, the diameter is about 18 centimeter, but some trees are less, sometimes bigger. And actually, we rented this research plot from the other research project. So the trees around the stand were cut down just before setting our plot. So also some trees were removed to make a thin plot. The right figure shows the final setting. The control plot had trees with 3,000 stems per hectare, and the thin plot had trees with 1,500 stems per hectare. In the plot, 2 kinds of sensors were inserted. One is a strain gauge attached to 2 directions of the stem base of 36 trees. The outputs from the sensors were converted to the maximum turning moment. Another is an inertial measurement unit, IMU, which consisted of 3 individual sensors, accelerometer, gyroscope, and magnetometer. So a smartphone has the same sensor inside. So if you have a smartphone, so your phone knows where it is and which direction it is facing. So this sensor, IMU, showed how much and in which direction the tree crown swayed. Here is a map of trees in the plot. A minor power problem occurred during the typhoon, so some data were missing. The trees with blue and orange circles provided the strain gauge and IMU data. The red circle indicates the damaged trees by the typhoon. From 30 September to 1 October 2018, a super typhoon named Chami made landfall in Japan and caused damage to not only forests, but also a lot of infrastructures in Japan. Our plots were also damaged. It was sad because expensive ultrasonic anemometer was completely broken and some trees in the plot fell over, like this photo. But luckily, we got the data to answer the question of what was happening to trees in forest during the typhoon. So I plotted wind speed, mean moment of flux, and how much the tree leaned due to the wind. What I want to emphasize is we found damaged trees only in the thin plot. Also, the damage occurred at the same time. As you can see, when the wind speed suddenly went up, it's a first the graph with 2 circles. Some trees largely leaned. There were also undamaged trees in a thin plot. We determined which trees were damaged or not based on the tree pruning experiments conducted at the end of this project. I want to present the results from the experiments today. but they provided the maximum angles when the tree fell over. As you can see from the green line on the second graph, although these trees seem to be normally standing after the typhoon, they had never been back to their original vertical positions. So the green line did not reach 100% after the typhoon. This indicates some of their roots had been broken. They were standing but injured inside. Again, nothing happened to the unthinned plot. They swayed, but not so much. And they returned to their original position after the typhoon. So the blue line reached 100% after the typhoon. So you can see the post-typhoon condition in the video as supplemental data for the published paper. So now let's look at a single tree movement during the critical 10 minutes from 110 to 120 on October 2018. The damage occurred during these 10 minutes. I plotted the crown positions. The yellow color on the graph indicates the high density of position. So the crown is often located at or around the yellow position. And I plotted as red dot the maximum turning moment at the stem base every 10 centimeter distance of the crown from the original position in the south-north and east-west directions. These two trees were undamaged. The left tree from the unthinned plot swayed, but the stem often stayed in the center. The turning moments vary because of many crown collisions with the neighboring trees. So because it was very dense forest, the right tree from the thinned plot swayed more than the left tree. The turning moment linearly increased with the leaning of the tree. So this tree did not have many crown collisions, which means it freely swayed. I showed two more trees. They were damaged in a thin plot. Both swayed much more than the undamaged trees. Also, in the left tree, the turning moment suddenly dropped, which means the main root might be broken. In the right tree, the turning moment did not increase so much, although there should be higher stress at the stem base with the leaning of the tree. This would indicate several roots, maybe not the main root, but gradually broken. Although the manners of root breakage seem to be different, again, these trees were damaged at the same time. I also calculated the number of crown collisions using the IMU data. For example, focusing on the stream-wide direction, south to north, from 1 to 2 a.m., 1 October 2018, the trees in the unthinned plot crushed each other with about 50% chance. In other words, in this hour, they attached to the other crowns for more than a total of 30 minutes. However, with the trees in the thin plot, the crown collision was only a 10% chance. So the trees in the unthinned plot supported each other, whereas the trees in a thin plot have to handle strong stress individually. So here is a brief summary. So we confirm the forests just after thinning are much more vulnerable to strong winds because it reduces the chances of crown collision. The trees fell over due to instantaneous strong wind, the gust, although the manners of root failure were different. The final topic is the challenges for the future to manage sustainable forest. I was thinking of how our findings contribute to solving actual problems. We all know thinning is an important forestry activity in order to enhance tree growth and biodiversity and to bring extra income to forest owners. But what if strong tropical cyclones, typhoons, come just after thinning? It sounds very bad luck. What should we do? What should we prepare? Once crown's close, it will be okay, but it takes a couple of years after thinning. So a new question is, how much crown closure is necessary to reduce wind damage risk? From our research, IMU sensor is useful to determine the crown position, but we have to attach IMU one by one, and the data becomes huge, and it's not easy to manage all data. It sounds not practical. So I'm looking for other ways. Do you have any suggestions? Finally, I should return to forest management. So actually, it's my first field. I was a forest manager before entering graduate school. So I am interested in the connection between science and practical activities in forestry. So what our research can contribute is for forest managers and forest owners, if we know suitable tree density or the degree of crown closure against strong winds, we can suggest how many trees can be thinned, where the best time to be thinned or harvested first, and when is the best time for management practices. For policymakers, we would give possible management strategy to reduce wind damage risk, scenarios of future forest resources, and suggestion for long-term support plan to stakeholders in order to make their forest more sustainable. Now we have an ongoing project. So this year, the last year, the second project, so it's for understanding the dynamic response of a whole tree, including stem and roots. In 2020, we inserted strain gauges on both stems and roots, and we have measured stem and root movement since then. I hope I can present the result in the near future. So thank you very much for your attention. For this project, I'm working with these people. Okay.
Thank you very much, Kana, for an amazing presentation that followed on really well from the previous one, where Thierry looked at individual trees, and you looked at the importance of considering several trees together. I think while we change over, if there's a question or two, one question for Kana, we could put that in, and if you could stop your share, and Eduardo, if you could set up. Is there any question online? Oh. Sorry.
Can you see my screen?
Yes.
You tell me when I'm ready to go.
Because it's his question.
Oh, Eduardo, so you had a question, I think. So do you want to ask your question before you start your presentation?
Oh, sorry, because I understood that I should put mine. No problem. Oh, my question.
Yeah.
I wrote something on the chat. It has to do with the unbalanced that when you thin a forest that has grown all together, no, the root system of each individual tree has certain characteristics that are related to the density. If you reduce the density in the first year or so, the root system has not developed to the new crowding conditions, so they are typically smaller and they're more prone to uprooting. No, so one possibility is to ask, can we increase the root development in preparation for a hurricane, no? Instead of waiting 5 years, 6 years for the trees to adapt? It was just a comment and a little bit of a question.
Would you like to say anything to in response to that?
That is great. That is great. Your question, and it's a very difficult one. Yes, we have to think about connection between above ground, that kind of like a density, the Thierry said, it's everything. But also the problem is we can't see it underground. So now we try to connect to measure the movement at the same time. But yeah. But why I speak about tree density is, for foresters, it's much easier to understand the forest, like a stand density is very obvious how to manage, or how can we get the log or everything. So I try to find, of course, the scientific background, but I also want to transform to such a very complex scientific thing to the more like a reasonable, more easy, more everyone can understand. It's a common sense. I didn't answer your question, but it's an ongoing project.
And thank you very much for that, Kana. And that's part of the purpose too of this webinar, is to get people from different disciplines and with different ideas together to talk about things relating to the impact of wind on forests. And now I think I'll hand over to Eduardo. So Eduardo Somarriba, he is a professor of tropical agroforestry at the Tropical Agricultural Center for Research and Higher Education, with the acronym CATIE, in Costa Rica. He's currently a fellow, MAK'IT fellow here at the University of Montpellier. He has decades of experience in working in agroforestry systems, and will share some of his observations of adaptations in agroforestry systems to tropical cyclones, or hurricanes, as they are called in his part of the world.
That's right. Okay, let me share my screen with you, and I thank you, Gunnar, for inviting me to share some of field experiences, because it's what they are, basically field experiences. I realized that in agroforestry, we don't have a systematic research on adaptations in agroforestry to hurricane or cyclones, and this is something that for the future will be a very good area of research. So I will talk about cyclones, trees on farms, and agroforestry, and I will start taking a look at where trees and forests occur on Earth. If you look at the classification, land use classification by FAO, you can see that the total land in the Earth is separated from water, and then they classified the land which is covered by forests and everything which is not covered by forests. That includes other wooded land, mostly tree crop plantation, and another category they call other lands. And when you make a zoom into this third group of land categories, You see that there are two major areas, land without trees because they are too cold or too wet or too rocky. And then there are areas, other lands that have trees. And those areas have trees, what they are called trees outside the forest, or TOF. When you zoom on the trees outside the forest category, you realize that these trees outside the forest appear in three basic categories. Farms, trees on farms, trees in the urban environment, and also trees in some natural plant formation, which characteristics because of the dryness or temperatures do not let them to be classified as pure forest. We're going to focus more on the trees on the farms in this presentation. I'll try to move this, is kind of taking longer. So you can see trees in the urban environment. There is a lot of knowledge about how to deal with trees and the environment and the urban environment when hurricanes hit. If you go to Miami, for example, all these areas in the eastern coast of the United States, South United States, you will see a lot of work on trees and the urban environment. But we're going to focus only in this presentation on trees on agricultural land. This is a picture from Nicaragua, and this is basically an agricultural landscape, and you see trees everywhere. But when you zoom into this landscape, you realize that the trees are in different land uses, and they might be in pasture land, they might be in home gardens, they might be in a coffee or cocoa tree crop plantation, and many other scenarios. One important thing that I want to say in this presentation is that trees don't like cyclones. And I want to say this because I'm going to focus on some of the ways people have taken advantage of the effect of hurricanes, and also to deal with some of the negative consequences. But it may give you the impression that cyclones are very good for agroforestry. I don't think they are, but farmers have managed to find ways to take advantage of some of the consequences of this. Trees really don't like the cyclones. When you try to move ahead with this, let me see, why don't it's not moving? Wow, why is not moving? Oh, I don't know what's happening.
Would you like me to, I think you sent me your presentation.
This is wow. This is not moving.
Do you want, would you like to stop your share then? And
I have to share, stop sharing, yes.
And I go in and okay, that's where you were, right?
Yeah. So go to the next. Yeah, so I'm gonna take the rest of the time to look at two basic examples of how agroforestry systems respond to hurricanes. One of them is cocoa, but also applies very much to coffee, and see how farmers have really taken advantage of this. Next one, please. Obviously, there are different ways farmers grow agroforestry with coffee or with cocoa, and this has important consequences in how they respond to damage, as we can understand from Kana's presentation. No? The density of the tree stand will influence very much how they respond to the same amount of wind. And some of the system go from very dense shade canopies, like the one here at the bottom, to very sparse canopy, and then the wind will be affecting individual trees more directly than when they are crowded. Next one, please. We'll give you some examples from Jamaica. Next one. Trees obviously fell over the plantation, and tree crops like coffee and cocoa that are in the understory are affected by these big trees falling down on them, with some very clear damage. Like next one, please. Trees are bent down and uprooted sometimes. This is a cacao plantation in Jamaica. In response to this damage, the tree will produce new suckers and create like a copious plantation of cacao, which is very inappropriate for agronomy because it increases the crowding, and to increase the crowding, some problems are associated with the diseases, especially fungal diseases that are somehow stimulated by high ground density will be increased, like Phytophthora or Moniliasis or witch's broom. So this is an important problem, and farmers have to spend a lot of money to control this, the shape of the density of the plantation. Next one, please. For example, these multi-stem trees is something that you don't want in the plantation because of this effect, no? Because the branches are close together, and most of the cacao fruit comes from flowers on the trunk, which is a characteristic, and the branches, which is a characteristic of a very few families in the plant kingdom. They call it cauliflorae, in which the flowers are on the stem, and if the stem are too close together, then the crown also gets very dense, and then problems with diseases will be higher. Next one, please. Obviously, a direct consequence of the damage is the breakage. The branches or the stem of the trees will fall on the cacao plant and will break the plant, and this has important consequences on yield. Next one, please. What is evident is that when this happens, there are different levels of damage, and you have to understand the different categories of damage that is inflicted to the cocoa plant because of the felling or the fall of the trees on top of the cacao plant. And these categories of damage really are a measure of the time it takes to return to the previous condition. Or sometimes the damage is so high that you have to really remove the entire coffee tree and plant another one. Will take longer time and will be more expensive to do than if the damage is only, for example, to break the canopy, to break the crown. You can prune it very severely and the crown will be ready back into production, let's say 2-3 years later. Whereas if you have to plant the tree, maybe it takes 7 years, 8 years to go back to the original condition. So this level of damage is something that we have to measure, and obviously that depends on what kind of tree species you have, the density and the characteristic of the species, the wood density, or the crown size and tree height, all these factors that Thierry talked us about before. Next one, please. Because of the damage, farmers say, well, I have this felled tree on the ground, let's use it. And this is one of the advantages that we'll see, because sometimes it's very difficult to get permission to cut a tree in a farm. This is the opportunity to do it. Next one. So you will see after hurricane, there will be a lot of commercial activity taking place in the agroforestry plantation. No? The timber will be processed and sold or used in the family. Next one, please. Firewood will also be collected and sold out to generate additional income to the farm. Next one, please. The thing is that it takes a lot of money, and all this income that is generated as a consequence of the tree felling and tree damage in the cocoa plantation is one way to help farmers themselves in paying for the repair of the plantation to the previous condition. Next one, please. There are other ways they can use it. For example, when the tree is damaged, they prune the cocoa tree, as you see in the right-hand side of the slide, and they use the tree architecture as a supporting living structure for the cultivation of yams. All those leaves that you see growing around the tree are basically 1, 2, 3, 4 yam plants that are planted using all the mulch that has been collected from the tree that was pruned. And then this mulching serves as a fertilization for the yam that grows very well. And then the tree stem and branches are used for support, as supporting material, supporting a stake for the yam. And then they can collect maybe 40, 50 kilos of yam that is good for food security at the farm level, or also for selling and then generate some income to the farmer. Next one, please. They can also do some management practices, some silvicultural practices to minimize the damage. Next one, please. For example, in Costa Rica and also in the Caribbean side and also in Jamaica, you see this practice. Some of the shade trees are lopped severely to reduce the crown size, and also they are kept low to reduce the cost management, and also to reduce the height, also reduces the effect of the damage of the trees on the coffee plant. Next one, please. The same thing happened with taller trees like fruit trees. This is example coming from Haiti. Farmers in Haiti let the mango trees, which is one of the most common tree species in coffee and cocoa plantation there, to grow big, which is unusual for a fruit tree. You want a tree to be short, but they want to be grown big because there is a huge market value for firewood and charcoal. So they decrown entirely the trees because of the damage or prior to the hurricanes to process all the wood into charcoal and sell it to the market, and then avoid the damage inflicted by the hurricane by having only trees that only one stem and very short stem, and there is no crown, to reduce the torque. Next one, please. You can also take another more dramatic example. This is come from the Caribbean side of Honduras. It takes a lot of effort. Next one. Many pictures that you see when you see a hurricane effect, you see the devastation, but one standing element in the devastated area is the presence of the palm trees. And probably Thierry can tell us very much about why palm trees withstand damage much better than most other angiosperm do. But the fact is that because of this capacity to bend and to withstand the damage, over the long run, palms tend to be overrepresented in the landscape. And I will give you some examples with this in Cuba, which is the Roystonea regia, locally known as palmiche in the Cuban landscape. Next one, please. This is what you see everywhere in Cuba. You see this palm, and because of the presence there, it's not only because they withstand the hurricane, but also withstand fire. There's a lot of fire problem after the hurricane hits an area because you got all this wood on the ground, there's drying, there's dry area, so you have fires. And also these palm trees are resistant to fire, and also they benefit in the germination because of the fire for the seed. Next one, please. Because of this, the presence of this palm everywhere in the landscape, farmers have learned how to use it. And one of the major uses is basically the fruit. It's palm oil, very important oil, and also very important feedstock for animals, and also the leaves. Next one, please. This entire culture in Cuba around climbing the street, there are contests, national contests in different regions, to see how people can do it in a better or faster way to collect the fruits and the leaves. And they're used basically for home consumption, like construction or rural construction. Next one. But also it has managed to go into the market. I mean, you can see minor, small companies who produce this leaves for selling to the touristic industry, which is one of the major economic pulses of money in Cuba. Next one, please. Obviously, feedstock for animals, especially pigs, but also chicken, is very important. You can feed the animals directly or graze them in the forest. Or next one, please. Or you can collect it and process it as a feedstuff, like in this particular example, which is all the bunches of fruits are collected, dried, and then processed into concentrate for feeding pigs and also feeding poultry. Next one, please. So I want to conclude my presentation with a few remarks. One is that cyclones seriously damage trees and tree crops on the farms. But the farmers have found ways to manage the trees to reduce or repair the damage caused by cyclones. Some useful trees increase their presence in the farming system, and because of this, farmers have developed a lot of knowledge, to manage the trip affected by hurricane, and also to make commercial or financial or land farm use benefits from the products of this species. Because of this, there is a rich traditional knowledge that need to really be collected and shared with many other places, for example, and also gives us the attention to stimulate the policymakers to find ways to facilitate the utilization of all these tree products in the farms, to help farmers to recover quickly and faster from the damage. Next one, please. So this is what I all have to say. I think I went 1 minute above my time, but if there were more questions, maybe we'll leave it to the end. Next one, please. Thank you very much.
Thank you very much, Eduardo. It were really important insights about how people are already adapting to cyclones. So led on very well to Kana's presentation before, where she was pointing out some of the ways how forestry could better adapt to cyclones, typhoons, or hurricanes, whichever part of the world you're in. So thank you very much for that. And as Eduardo mentioned, any questions, please wait till the end. We're not too bad in our time at the moment. So I would like to move on to Ted, Professor Edward Webb, who is at the University of Helsinki in the Department of Forest Science and the Institute of Sustainability Science. He's a leading researcher in tropical conservation ecology. And with regards to cyclones, he has collected probably one of the best data sets to investigate the impacts of cyclones on rainforest and their subsequent recovery in the long term. So without further ado, I hand over to you, Ted.
Thanks. Can you hear me? Can you hear me okay?
Yes.
Okay, and you got my screen. Okay.
Yes.
Well, first of all, it's a pleasure to be here. I'd like to thank Gunnar and Tomas for the invitation. And I've really enjoyed listening to these diverse talks. I think the sequence has been really informative as well. What I'd like to talk about in this short presentation is a long-term monitoring project that we have in the South Pacific, looking at forest dynamics, and in particular, the recovery of tropical forest from a cyclone that occurred in our plots. So this project has been worked on by myself and a host of people, as you can see on this first slide here, and I'd like to acknowledge both their work as well as the funders that you see on the bottom. So I'm going to talk about the South Pacific archipelago of Samoa. It's located in the South Pacific, as you can see on the top left here. It's a hotspot archipelago, much like Hawaii, stretching from Savaii all the way through the Manua Islands to the east there. Back in the 1990s, when I was a lot younger than I am now, I moved there and worked as a botanist, living on the island of Tutuila, setting up some long-term research there, and then also on the island over here in Ta'u. And as you probably guessed, being in the South Pacific, the Samoan archipelago is frequently struck by cyclones, perhaps not as frequently as some of the other parts of the Western South Pacific, but it's had a number of cyclones occurring in the last 50 years. So if you've lived there, you've definitely experienced several cyclones over the course of one's life. Now, in the year 2004, the National Park of American Samoa asked us to establish some long-term forest monitoring plots on the island of Ta'u. So the archipelago is divided into two groups politically. In the west is the independent country of Samoa, and on the eastern half is the what they call the American affiliated islands of Tutuila and the Manua group here. So in the mid 1990s, we set up long-term monitoring here, and then in 2004 we were asked to set up monitoring plots here on the island of Ta'u to monitor forest and habitat condition, mostly for wildlife, birds and bats, to get baseline information on the forest dynamics. And if it ever happened, at least in the near future, the goal was to be able to monitor the recovery of the forest from cyclones. So we set up a total of 6 hectares of permanent forest plots on the island here, separated into previous land use. We had 2 sets of plots that were old plantations, which are dominated by breadfruit, Artocarpus altilis, as well as coconut, papaya, and other agroforestry species. And then we had 2 plots that were mature forest, or at least were as close to mature forest as we could find, which had not been under these agroforestry systems, at least for the past 50 years, or in the lifespans of anybody that we had talked to, or in the historical record. In these plots, what we did were very standard forestry methods. We divided the plot into 10 by 10 meter subplots, and we identified, mapped, and measured the tree diameter of all stems above 10 centimeters. Later, we also added sapling plots where we measured all trees from 1 centimeter diameter up until 10 centimeters in diameter. So we have a pretty good record of all the trees that existed in 2004 and then since that time. This is an example of what the plots look like, or what the trees with the tags look like it. Now, our plots differed in their species composition. In the mature forest, it was dominated by sort of the standard long-lived secondary successional species, Alphatonia ziziphoides, 2 species of Disoxylum samoanth and Diospirus samoanth. In the old plantation, here you can see the remnants of human impact, Artocarpus altilis, Cocos nucifera, as well as Bischoffia javanica, which has a lot of cultural value as well. In the old plantation, you can see there are several which are considered to be not native to the archipelago, which were probably introduced by Polynesians when they arrived. Now, we set up our plots at the end of 2004, and as luck would have it, 2 months later, Cyclone Olaf, which was a Category 5, passed within 20 kilometers of the coastline of Ta'u. Here's the island. Here's the eye of the cyclone as it passed through. It went in this direction here. So we had a very fortuitous natural experiment, before-after experiment that was set up. So basically 2 months after the cyclone, or 4 months after we finished the first survey, we revisited our plots, and this is what it looked like 2 months after the cyclone hit. This is one of the researchers, Saifoi Fa'aumu, who is probably about 1.5 meters or 2 meters above the ground. We virtually walked on downed tree trunks most of our resurvey here. We ended up finding every tree, if you can believe it, except for, I think, 5, which were all papaya, which got blown to smithereens. But everything else we found. We categorized the damage to the trees, whether being uprooted or snapped, very standard practices here. And then we started monitoring the recovery. Now, we looked at the variation across tree species to resistance to the structural damage. In this graph here, this figure, you can see here are the most common species here on the y-axis. The x-axis is the percent of the of the population that was damaged, either by snapping or by uprooting. And you can see a pretty wide range in susceptibility to cyclones here. So, for example, Pipteris macaranga, very much early successional species. Basically, everything was damaged, but they tended to uproot more than snap. And down here at the bottom, we can see some of these more late successional species like Syzygium, Flacourtia, and Garuga, which only sustained about 25% major damage. All the trees, if they weren't blown down or snapped, had their leaves completely removed. So all the trees in some way sustained some damage. Now, what we're asking now by this long-term monitoring is we've gone into this questions about what is driving survival. How does this initial damage affect the long-term survival of tree species? So how variable is survival across species, both those that are damaged and those that were not damaged? How long does the cyclone affect this survivorship? Is it an immediate change in survivorship, or does it last for many years? We're looking at how community composition may vary over time after the disturbance, and what may be driving or associated with species-wise population responses, what we call vital rates, basically mortality and recruitment after the cyclone. So I'll give these 4 results in the remainder here of the talk. Just to give you an idea of the survey intensity, here you can see this is a timeline since the year 2004, since we began. Basically, after the cyclone, we went every 18 months to resurvey all the plots until the year 2016, and it has started to spread out a little more less frequently for reasons that you'll see soon. And this here we have 2023, and basically day after tomorrow, I'll be heading on a plane to the South Pacific to resurvey our plots there. So we'll have almost a 20-year time series. So here's the first set of results. This figure shows 25 species, the most common species in the plot. We divided up the individuals as to whether they sustained major damage, which is snapping or uprooting, versus those individuals in the species that only had either some branches that were broken or that lost their leaves. So the green means they did not sustain major cyclone damage, and the red means that they were either blown down or snapped. And this is basically the survivorship curves. So 1.0, since they were all alive in 2004, and we were monitoring their populations over time. And you can see some interesting results here. You can see, for example, if you look just at the green lines, which we might call the background mortality or background survivorship rate, they vary across species. So for example, we'll see Roost titensis here, which has a sort of continuous decline even in individuals that were not damaged by the cyclone. Whereas something like Dystrophia javanica had almost no loss of mortality from the year 2004 to the year 2016. Same with Syzygium and Trichulia, etc. And then you compare that to the red survivorship curves, and you can see basically there are some species that were very strongly affected by the cyclone, their long-term survivorship curves, but some basically showed no impact of the cyclone, such as Hibiscus ciliaceus here, Artocarpus, the breadfruit, Dystrophia, and even Roost had a very little apparent impact of the cyclone on their survivorship. To look at the population dynamics, we looked at, as I mentioned, the vital rates, recruitment, and mortality. So here are the vital rates over time for essentially the same group of species. So if you start seeing green, that means you had recruitment events. So this is Carica papaya, which is papaya, Cordia aspera, Macaranga harviana, Dipterus argenteus. This is the recruitment of trees, meaning those that are greater than 10 centimeters in diameter. So it's not going to be an immediate recruitment event. That's why you see at least one bar in between when the cyclone hit in 2004 and the recruitment for some of these species, because it takes time for them to get 10 centimeters in diameter. We do also have data for saplings, and it looks very similar to this. But you can see some huge variation in some of the species here. But by and large, what interested me with this is that we see very little change in some of the species population dynamics. We don't see increases in mortality. We don't see a huge recruitment event after such a substantial damage. There's one species, Trichosperma richii, which basically blinked out of our plots. There were only 20 individuals, and I haven't seen one since. 3 species that exhibited the most recruitment after the cyclone are the usual suspects, Macaranga, Pipterus, and Carica papaya. And if you look at those data over time, this is the relative abundance of stems over time. On the x-axis are the years of survey, and the y-axis is the relative abundance. So everything sums up to 100%. Here are the major tree species, color-coded on the right side here. And you can see, if you compare, for example, Artocarpus, or you look at something like this orange, which is Hibiscus tiliaceus, their relative abundances, which would be the width of this stacked stacked graph here, it doesn't change substantially. But what you do see is something that aligns very much with successional theory, where you have huge increases in certain species, which then have high recruitment and then high mortality rates. But in this case, it was actually a two-phase successional process where you had papaya, which comes in first, becomes a substantial proportion of the community, and then basically dies out. And that is in parallel with the increase in Macaranga harveyiana, which then, after a few years, dropped out again. Now, this means that about 10 years after the cyclone, the relative abundance of species essentially returned to what it was prior to the cyclone. So there's some reorganization dominated by 2 or 3 species, but then it basically went back to the way it was in terms of structure. So what are some of the driving factors in this recruitment and mortality and recruitment? Well, we're taking a functional trait approach. Here are 4 functional traits that we collected data from in the field. We collected functional trait data for about 50 species. The seed length, the SLA, specific leaf area, wood density, of course, and the 95% size distribution in terms of diameter. So we used data not only from the island that we were working on, but also some of the other islands here. So we think that functional traits have an important impact, as we're already learning, on both the resistance and the resilience of species to these cyclones. In the literature, it is known quite widely that these functional traits do correlate. So we did a principal component analysis, even though we only have 4 traits. By putting them through the PCA, we actually ended up with 2 major component axes, where one axis has to do with the size of the tree and the size of the seeds, and the y-axis relates to the wood density and the specific leaf area. So when you plot all the species in this 2-dimensional space, it spreads out quite nicely. So up here in the top left, you'll see large trees with very low wood density. Down here in the lower left, we have small trees with low wood density, large trees with high wood density, and small trees with high wood density. And we can use those PCA scores as predictors in subsequent models. So this is what we did. And these are just very simple models. Actually, we just ran a correlation analysis. So we tested the 4 hypotheses that I listed in the beginning, or about 10 slides earlier. And let me just go through them here. The first hypothesis we tested was that the functional traits are associated with mortality or with recruitment. And so since we had wood density on one PC axis and species size on the second PC axis, we can just use those scores as our predictors. I will only show you the significant results here. What we found is that there was a negative association between wood density and mortality. And this is what we would have predicted from the literature. It's sorry, not wood density, large maximum diameter. Excuse me, I said that wrong. Right. In this case, PC2 was the only one that was significant. So larger species had lower 10-year tree mortality. Our second hypothesis was that abundance drives the vital rates. So in other words, the more abundant the tree, the higher the mortality is going to be, or the more abundant the tree, the higher the recruitment is going to be. What we found, the y-axis in both of these figures is the same. It's recruitment, but on this side here, it's for the trees, 10 centimeters in diameter. On this figure over here, it's the saplings. In both cases, we see that there is a positive relationship between the abundance of stems prior to the cyclone in 2004 and post-cyclone recruitment. Perhaps surprisingly, we did not see an association of abundance with mortality. So more abundant species did not sustain more mortality than rarer species. but they did experience greater recruitment after the cyclone. The third hypothesis is one that we do see in the literature, and it has to do with compensatory recruitment. And it has to do with how rare species may be able to sustain themselves or persist at very low densities. And one hypothesis is what we call compensatory recruitment. And that says that rare species are able to regenerate at a higher rate relative to the more abundant species. So in other words, species that are more prone to be negatively affected by cyclones are going to have higher recruitment. So you can be rare or you can be very susceptible to damage. In either case, you need to have higher compensatory recruitment, or you have to have compensatory recruitment to respond to the cyclone. So we were looking at the difference between survivorship for those individuals in the species that did not sustain damage and those that did sustain damage. So it's basically the gap between these two lines at 10 years after the cyclone. That's going to tell us how susceptible that species has been to cyclone damage. And then we associate that with recruitment. And what we found was that the greater the difference between survivorship of those individuals that were not damaged with those that were damaged, the greater that difference, in fact, the lower the recruitment was. So this was the opposite of what we expected. We expected to see a positive relationship such that the more susceptible species had higher recruitment, but we found that the more susceptible they were, the less recruitment they had overall. So this is a kind of a counterintuitive result. So to summarize the conclusions of this work so far, we saw that this was a very large cyclone, category 5, and that there was huge variation in damage rates associated with some life history events. Life history traits. Post-cyclone vital rates varied widely. However, total species abundance sort of remained very surprisingly stable, and the structure returned within about 10 years. So I would call this a high resilient environment. And finally, post-cyclone regeneration looks to be associated with adult abundance, meaning that the more abundant the species were, actually the lower the recruitment have. And this suggests that in a changing climate where you have more intense cyclones, you're going to have a situation where the rich get richer or the abundant get more abundant and the less abundant become rarer, or the more susceptible become rarer. So that is a potential policy implication there. So that summarizes the work that we've been doing. I'm happy to take any questions. Thanks again very much for the invitation, Gunnar and Thomas.
Thank you for an exciting presentation, Ted. Are there any questions for Ted? So I thought it was a very, you can enter them through the chat. So that was very exciting and definitely showing that changes in our forests are afoot if cyclone strength and frequency should change.
I would think so, and it would be, if we have ecological modelers, this is something that has been sort of a dream of mine, is to get some type of, forecast modeling. Since we do have a pretty good data set now, I think that's amenable to something like that.
There is a question for you online from Kana. He said, you didn't say much about native and non-native species.
That's good. We actually haven't analyzed the specific changes in non-native species. So on the island of Ta'u, the invasive species that are there were not actually in the plot. So Artocarpus altilis is naturalized. Pischophia javanica is naturalized. Coconut is not even really naturalized. So these would not be considered aggressive invasive species. On the island of Ta'u, you have a couple of species like Adenanthera pavonina, which it's not aggressive either. So this island has been very fortunate to not be dominated by invasive tree species. The worst, of course, is Clydemia hirta, which is found all across the Pacific, but that becomes very important once you get above maybe 300 meters elevation.
What about Carica papaya, which would be non-native?
So that's good. I mean, so how would I look at Carica papaya? I would look at it as something that actually, I think overall it may be a net benefit. First of all, they survive only in very high light environments, and I don't think they're replacing anything, because you saw Macaranga harviana, which is the native early successional species, come in, but it came in after. I don't know if papaya was out competing it and suppressing the regeneration. What papaya does in these forests actually is it is an important resource, or it is used widely by Samoan starlings and Polynesian starlings, and they are the seed dispersers of it. So it actually sustains wildlife populations after a cyclone.
There's another question for you in the chat. Can we say that tropical cyclones might reduce biodiversity in tropical forests? And that's by Kana and Kamimura.
I saw you got a tough question earlier, and now you're giving me a tough question, so it's being passed on. I don't think we can say that based on this research, because our relative abundance values basically remained unchanged. We did, like I said, we had one species, Trichosperma richii, which had 22 adults, which are no longer in our plots, so that could be susceptible. But overall, that is a loss of one species, which I don't think is going to qualify as having major reductions in biodiversity. So based on the data that we have on one cyclone, of course, I'm not sure. I think you would have to model it, right? You would want to do, several hundred years of modeling to try to find out what might happen overall to the species diversity based upon the vital rates that we have and the damage rates.
Thank you, Ted. Are there any other questions?
Yes. Okay. Yeah, there's one more. Apart from life history traits or vital rates or tree size and wood density, are there other mechanistic traits that would determine species resistance? Well, yeah. So I was very interested with Thierry's talk. Very interested in that, because that seems to be somewhat species. It kind of ignores species, or it may just be a constant mechanical thing, which I hadn't really thought about. I was only looking at species specific traits. One thing that we did find was that the likelihood of survival after snapping was related to the height at which it snapped above the ground. So the closer it snapped to the ground, the less likely the individuals, regardless of species, were expected to survive. And when Thierry said that you with the damage, the snapping frequency of height above the ground, they don't snap closest to the ground. This is exactly what we found. We found that basically at a meter above the ground is where we had a lot of snappage that occurred. And I don't think that's related to the species. Might not be related to the species now that I think about it.
And there's yet another question. Did you compare mortality rates of undamaged trees in damaged forests versus in undamaged forests in your Tutuila plots, for example?
Good question. Well, not in this presentation, and I know we have it. I cannot think of the numbers on the top of my head. Sorry, Thomas.
So if there are no more questions, so thank you very much again, Ted. Just wanted to mention too, I think Thomas and I and others, we looked at species abundance distributions, and we also found in different plots after cyclones, and we also found a bit of a homogenizing effect. So, there's yet another question. No, that's That's a comment, sorry. So with that, I think we can, that's a really good segue to move on to our last, but definitely not least presenter. And that's Thomas Ibanez, who is my host over here at AMAP. And he's part of the French Institute for Research and Development and one of the most exciting young researchers in the field of tropical ecology. And in the field of the impact of cyclone disturbance on forests, he's probably already one of possibly the leading researcher already. And he'll be presenting a work that he's been spearheading over the last couple of months, and that's the development of a new R package that will allow basically calculating the impacts that cyclones are having in terms of wind load and energy load anywhere, anytime. Anyway, over to you, Thomas.
Thank you, Gunnar. Can you see my screen?
Yes, and we can hear you very well too.
Great. So thank you for the introduction and hi, everybody. So yeah, for this last talk, I will introduce you our package we are working on since several months now, and it has been speeded up by the coming of Gunnar with us in the unit. So the recipe for this package was 1/3 of developers with Baptiste and Thomas Arsus, 1/3 of physicist and oceanographer with Swen that we heard this morning and Christophe Menkes. And the last third was ecologist with Gunnar and I. So we basically developed this package to transfer knowledge from physicists, oceanographer to ecologists or other people that want to better take into account cyclone behavior and regime into their analysis. So we developed this package to map the wind across space and time. So why are we developing this package? So it's, as I said, to better account for storm behavior and regime when analyzing the short, so damage, medium, response, or long-term impact like acclimatation of cyclones. And what it's usually done is simply use wind scales to estimate the potential damages caused by winds to forest or infrastructure. And the most famous one is the Saffir-Simpson Hurricane Wind Scale. So, for instance, for Category 1 cyclone, you can see that we have some damages to tree branches. And then Category 2, you have some trees that start to be downed. Category 3, we have large trees that get downed. And for Category 5 cyclones, like the one Eduardo Webb analyzed, most of the trees or shrubs are downed, actually. So this is nice, but one of the problems is it's very variable in time and space. So as Swen presented this morning, so the cyclone or typhoon or hurricane originates close to the equator, and then they move polewards, and moving poleward, they strengthen, and then when they reach cooler water, they get less strong. So we have a temporal variation in the intensity of cyclones, and also at a given location, we have a high variation when we move from the eye of the cyclone to the exterior of the cyclones. And also we have differences in the translation speed of the cyclones, meaning that in some area, the cyclone is lower, meaning that the ecosystem or structure will be passing the strong wave longer than in other places. And in the other point, it's the frequency of cyclone is very also heterogeneous at the global scale, and we can also expect that forests that are located in places where cyclones are very frequent are somewhat acclimated to those disturbances, and we will observe less damages than in places where cyclones are more rare and on species and ecosystem not acclimated or adapted. So the second point is we developed this package to enable comparative studies. So far, most of the studies are very local and focus on the effect of a specific cyclone on a specific forest. So for instance, Cyclone Waka in Tonga, or Cyclone Hurricane Hugo in Puerto Rico, or Gilbert in Yucatan Peninsula. And so we have also contradictory results into those different studies. And if you want to have a more comprehensive understanding of the impact of cyclone on forests, we need to be able to compare those studies. And to do that, you need to better know the behavior of the cyclones that affected those different forests. So it's a work we are conducting right now. So we compiled post cyclone damage survey across the tropics to compare the effect of cyclone of different systems. So here we have 9 cyclone and 11 studies. So we have the data from Eduardo Webb here. I also saw that Tanner was here, who shared his data from Jamaica. So thank you for sharing your data. And what we can see here on this graph is that the proportion of uprooted trees is quite well correlated with the maximum observed wind speed for a given site, but we have a big variability. So the idea now is to try to understand this big variability. And the last point is that we are developing the storm package to try to develop a predictive model for storm impact and resilience. So this results is from a publication from last year, where we analyzed the dynamic of NDVI, so the greenness in the Southwest Pacific along the last 20 years, I think. And we try to understand how NDVI changed after the cyclones and how long it took to recover. So we can see that for that we use some of the parametric wind model we implemented in this R package, and we can see that with the predicted maximum sustained wind speed, we can have a good idea of the impact on the NDVI and also on the time of to recover. So the idea is to develop such model for natural ecosystem, but we also believe that we can use parameters from wind behavior to predict impacts for forestry, agroforestry, or other systems. So how this package works? So first we need to access storm track database. So in the database, basically you have for each cyclone, you have the positions, the name, the year, and some statistics about the cyclone itself, like the maximum sustained wind speed, the radius of maximum sustained wind speed, and pressure data. So for that, we suggest to use the database from the IBTRACS, the International Best Track Archive for Climate Stewardship from the NOAA. And as they say themselves, this is the most complete global collection of tropical cyclone available. So it's the easy one to use. But then if you are interested in the more specific area, you can also use a more regional database. So this database is quite comprehensive since the 80s and the satellite era, and give observation for tropical cyclone every 3 hours. And you can go directly on this website to download the data with different subsets for the different basin or time periods. And it's totally open, and you just have to cite the sources. So the first function of our package is basically to load this database into R, into a format that can be used by the other functions. So for that, you have to use the def database functions, in which you have a dictionary to do the correspondence between fields. You also have a unit conversion arguments. But basically, if you use IBTRACS data, you don't have to do anything. You can just use the default setting. So once you have the storm track data on your computer and loaded in R, you can use the storm function to basically do queries on the data set. So either spatial queries using, for instance, a country or basin name. If you are most interested in precise points, you can use lat-long coordinates of precise points, or you can also import a shapefile. You can also do temporal queries, like if you want to focus on 1 year or two different seasons, or you can focus on a specific storm using its name. And so it will create an extraction of storms. And once you have this extraction of storms, you can use the co-functions, which model the behavior of hurricane or cyclones in time and space to compute time series or maps. So for instance, here I will show some example of how to use the storms and plot storm function to get and plot storm track data. So for instance, here, basically only specifying South Pacific, you can extract all the storm track data in the Southwest Pacific since the ATIE. How you can be more specific and specify a country name, a storm name, and a season, and you will have the track of the cyclone and all the data extracted for this particular area. Here is another example for Kana, for example. You can specify the coordinate of a place. Here I took the city of Tokyo. And so you can ask to extract all the storm over a study period that went nearby this point. So here by default, we use a 300 kilometers buffer. And finally, you can also load your own shapefile and make spatial queries using your own shapefile. So for instance, here I use the exclusive economic zone of New Caledonia to extract all the storm inside. So then the second step is to model wind field using parametric models. So basically it's model the radial wind speed as a function of the position of from the eye. So when you go from the eye to the outer, the wind first increase and then decrease. So we implemented 3 different models. So the simple one only use maximum system wind speed, latitude, and the radius of maximum speed. And the second one, Holland, use also the pressure data. And the last one, the boost model, is just a modification of Holland with asymmetry with the cyclones. So for instance, here I compared the three models for a particular time of observation. And you can see some differences in the wind field generated. And another point is the Holland and Willoughby model are symmetric, meaning that the simulated wind is the same, whatever the direction. But we know that cyclones are asymmetric, so we also added function to correct for that and add asymmetry to the model. So yes, it's an example of how we can add asymmetry to the Holland model using different methodology. So at the end in the package, you can have 5 different ways to simulate wind fields. So it's also a way to have an idea of the uncertainty of the outputs. Then we also implemented summary statistics. So we saw that wind change in space with the distance to the eye, but also in time. And for one point, we wanted to be able to integrate it, the wind behavior along the lifespan of the cyclone. So for that, we implemented 3 different statistics. The first one is the maximum sustained wind speed. So it's basically the maximum sustained wind speed observed along the lifetime of the cyclones. The second one is the power dissipation index, and it's basically the integral of wind speed along the lifespan of the cyclone. And the last one is the duration of exposure. and it's so you have to specify a threshold. By default, the function will use the threshold of the Saffir-Simpson hurricane wind speed, and for each threshold, it will return the time of exposure. That means the duration of exposure above a certain threshold. So, for instance, here I will show an example of how I use the temporal behavior function to compute time series and to compare different locations. So here in this example, I use the example of PAM, which was a major cyclone who impacted the Vanuatu in 2015. And I will compare the wind profile between the two main cities, Luganville and Port Vila. And you can see that the cyclones went closer to Port Vila, where it caused heavy damage. So here is the result when we compute the time series, and we can see that we have big differences in maximum sustained wind speed, with, for the same cyclones in the same country, maximum sustained wind speed being more than twice higher in Port Vila than in Luganville. And then if you integrate wind speed during time, then we can see that the differences between those places is even bigger. Now it's more about 8 times higher. And the last summary statistic is exposure. So if we set up a minimum wind threshold that's 33 meters per second, which is the threshold for category 1 cyclone, we can see that Port Vila has been exposed to such intensity wind during almost 10 hours, while Luganville didn't experience such wind speed. So we believe that those statistics might be used to better understand the variation of damages in our case in forests, but also to infrastructure or agrosystems. So the other main function is the spatial behavior function, which allows to map cyclone behavior and export rasters. So it's the same example with the PAM cyclone in Vanuatu, and we can easily compute and specialize the maximum sustained wind speed, the power dissipation index, or the direction of exposure here. And we can do that at different temporal and spatial scales. So by default, we use 2.5 minute spatial resolution and 1 hour temporal resolution. But you can use a coarser spatial resolution. And the grade we use are the same used by the WorldClim dataset. So you can directly use the output result to cross them with other climatic or environmental variables. So the last point, but not the least, is once you have simulate wind speed and statistics for all different cyclones, you can put them together and stack them to estimate wind regime across an area. So in this instance, in this example, I use all the storms for the last 40 years over New Caledonia, and I simulate the power dissipation index for each storm, and then I stack them and sum the power dissipation index. And when we can see that in New Caledonia, we have kind of north to south gradients in the energy received by forests along the last 40 years. So we are almost ready to submit this package to AirCran. It should be done by the end of the month, but the development version is already available on GitHub. So you can install it on your Air software using the DevTool functions. We also have a website with a full documentation, and please report bugs or enhancement suggestions on the GitHub website. So thank you, and I would like to thank also the Hammond Slate Foundation, which were able to fund the development of the package and especially pay for the work of Baptiste for developing this package. And also I thank the MAK'IT, University of Montpellier, University of South Australia, and AMAP to make the visit of Gunnar possible, and which helped to boost the development of the package. Thank you.
Thank you very much, Thomas. Any questions for Thomas? So yeah, as you can probably tell, we're pretty excited about the development of this particular package. So we hope that will drive research forward in filling some of the gaps, and also can work as a tool for analysis, not only in the ecological space, but also in environmental economics, social science, because you can now relate other observations in various other databases to the cyclone history of a particular location. I was just talking to give people time to ask questions, and there's a point from Edmund Tanner on a question on the chat, and his question is, I think your model does not include altitude or aspect, which would be important, I think.
Yes, it's a very good point. So the resolution of the model is quite coarse at this stage. So it simulates wind in flat area. It doesn't take into account topography. But then the idea is to add into the package a function to compute topographical exposure. And yeah, so it's the further development. And then I don't know, I think the better way to deal with topography might be maybe Swen can answer that, but maybe using downscaling model. So we can force the model with a regional wind speed generated by the cyclone, and then at the landscape level, we can use another model to simulate the effect of topography of wind. So I know that some people develop topographical exposure indices, but I'm not sure it works very well for what I saw in publication. So it's further development.
Thank you. Thomas, are there any other questions? There is one from Raphael Pelessier. Concretes for the Storm R package probably useful in many domains apart from ecology. It's more of a comment.
Yeah, and Gisela asked about the latitude within the equation. So I don't know if Swen is still here, but maybe Swen.
Yeah, I'm here. So regarding the latitude, actually, yeah, there is a latitude parameter in the equation, sure, because typically tropical cyclones are larger at a higher latitude than in the tropical band, and there's a latitude parameter that is included. And maybe I can also answer on the question of altitude that was asked before. Actually, there are existing sort of parameterization or extent of the profile, the wind profile with altitude that are generally used in the, for example, offshore wind farm area. So there are existing extension and actually, I think it really depends then on the height that you want to look at. And something to remember also is that parametric profiles are usually fitted to observations that were taken from aircraft that fly inside tropical cyclones and from simplified models that consider the wind balance above the boundary layer. So typically, the profiles are fit to winds that are above the boundary layer, and then they are extrapolated inside the boundary layer onto the surface. So we have already this kind of parameterization of what happened on the vertical. And we can also add some complexity on that. But let's remember that a tropical cyclone is a very high vortex that encompasses the full 15 kilometers. So we have the effect of the surface of the canopy, probably, for example, and the drag on the land. But there is also something that is really driven by the vortex itself, and it is encompass the full height.
Thank you. Are there any other questions for either Thomas or any of the other previous speakers before I will try and summarize things and maybe have a bit of a general discussion? Because I realized that, for example, for Eduardo, Thierry, and Kana, the time was very limited for questions. If okay. If not, so am I sharing my screen?
Yes.
Sorry. Okay, so if not, we can move on to the overall discussion. Sarah kindly already sent around a link where the presentations will become available very soon. And if you struggle finding that later on, please send me an email and my details are there. If you're on Twitter, I will also send a tweet when those different presentations become available. So before doing anything else, I thought that it might be a good idea to, I'm just checking, okay, yeah, to thank each one of you, presenters and other participants of this webinar for your time and for joining us. I'd like to thank MAK'IT again, and especially Sarah, who was here today and gave up her time to help out with the logistics, and Marianne Chamel and Brenda Hernandez also helped a lot with the logistics of this event. University of Montpellier for making this all possible. AMAP for hosting me, Thomas, and in particularly Thomas Ibanez, who, as I mentioned, is co-hosting this event, and my university back in Australia for supporting me during my sabbatical here as well. So we had 6 very good presentations that I thought fitted quite well together. So I'll just sort of first summarize the key messages that I got out of it. There were a lot of very important points. So Swen introduced the physics and climatic background of cyclones. And I think the main point, one of the key points, was all the uncertainty that is still there, and it makes it really difficult to forecast cyclones now, and even more challenging to predict what the future holds. Thierry gave us very important insights into the mechanics of trees and what the mechanical properties of a stem basically mean for the resistance of trees to wind, and not just the stem, but also the root system. Thierry focused mostly on individual trees, while Kana then looked at the impact, yes, on individual trees, but how joint swaying of trees and canopies being connected. So the density of forests actually helps moderate the impact of cyclones, and how that and the implications for that in the thinning process, which is regularly used in forestry. And she concluded with some recommendation for forestry practices. Eduardo then looked at some of the practices, how people, mostly in Central America and the Caribbean, have sort of already adapted to the frequent cyclones that they are experiencing in their agroforestry systems. And that sort of highlighted very much the importance of local knowledge when, well, in adaptations to cyclones, and if we need to adapt to different cyclone regimes in different areas. Ted then used an amazing data set for a forest system in American Samoa to basically give us some indication about what the impacts of cyclones are on natural forests, and suggesting that it can lead to homogenization, but also looked at characteristics of individual trees, such as wood density. And finally, Thomas presented on a new package that will hopefully that will allow us to model the impact that cyclones have at a particular spot anytime, or that can be overlaid to provide a cyclone regime for a particular reason, for a particular region. So Swen highlighted how much uncertainty there is in our predictions of cyclones, our forecasting of cyclones. Thierry and Kana also highlighted the complexity of individual trees, and also that they interact with other trees, and not just above the ground, but also below ground. And one of the key messages there was that there's limited knowledge in a lot of aspects relating to tropical cyclones, and that's something that Thomas and I have been finding when looking through the literature on a lot of aspects relating to cyclones. So one of the key messages definitely is that we would need to know much more and would need to invest much more time and research and funding to better understand the impact of tropical cyclones in a lot of different fields, because it's a very multidisciplinary field. And that would then help us to be better prepared if there are changes in the cyclone regime. We hope that that new package, Storm R, will lead to more studies on wind and cyclone impact, and can be very useful and will help to develop our knowledge in that field. But despite the limitations in our knowledge, we've also seen that people have already been adapting to cyclones, or that recommendations can be made for making our forestry sector and potentially our natural forests and agroforestry systems more resilient to cyclones. So I was wondering, as a question for the panel, would you just want to comment what your recommendations for the future would be?
Okay, maybe I can start, Gunnar.
Yes.
Thank you very much for all the presentations and for your synthesis. I would be interested by a particular question. I think that there's a lot of research works on shade tolerant species, for instance, or light adapted species, tree species. And I don't think we have a list of species tolerant to cyclones or wind, and I think that in particular in terms of acclimation, there are tree species that are very efficient in terms of acclimation to wind. But we don't know much about, I would say, what trees in tropical regions are well adapted or not in terms of, I mean, mechanically adapted. And this should be very interesting to, I don't know, maybe to analyze some data, if there are data, or I know that Thomas in particular has a lot of data, or knows where to find data that we could use to maybe to make or to go further in this topic.
Thank you, Thierry. And I think that is a very good and a very important point. And one of the things that Thomas and I have been realizing is that there is information in a lot of different areas, and that they all might have to contribute to it. But I do agree that there is a major gap in terms of sort of the resilience of trees to cyclones and the different aspects of that.
Can continue.
Also,
Yeah,
I think one of the consequences of this presentation from my own side was I take a quick look at the agroforestry literature and realized that we really never had a publication like looking at this particular issue in the agroforestry literature, despite the fact that there is a lot of effect of hurricanes in many places in the world to the agriculture there. I think there is a need to really collect that information, to think more about the issue, maybe have like a review or a summary or something that really put this information more available to the people. That's one thing. The other thing is it has to do with the traditional knowledge. I think there is a lot of knowledge how different communities in different parts of the world respond with managing their trees in their farms to the effects of hurricanes or preparation for the hurricanes. That is not really available, I would say. And also some issues related to policies, especially in some areas. For example, in the Caribbean, the use of timber trees in Caribbean island is incredibly restrictive, and ecologists and conservationists, I am an ecologist too, as by my background, but we ecologists and conservationists, conservation people in the Caribbean have really ended up with a very restrictive and very harsh legislation and behavior, institutional behavior toward the use of trees in farms, especially timber trees. And when these events happen, farmers really face a lot of problem to make use of the timber that is fell on the ground in the farms. And because of the permit, acquisition of the permits is so complicated, and most of this timber, wood farm timber, goes into the illegal channels. People use the timber anyway, only they don't ask for permission, but it's because it goes to the illegal channel, then the benefits, the people really get from it, it's not as good as it will be if this is a legal process. They have to sell it at a lower price, or they don't get all the benefits. So I think there is also some message for politicians here, how to make it better for farmers to make use of this timber in the farm.
thank you, Eduardo. It's a very useful point. And we were hoping to have another speaker on impacts on livelihoods, but he had to withdraw, unfortunately. But yeah, there are cascading impacts of cyclones in communities often, and managing those would be very important. Thomas, you wanted to say something before, and then I have a question from Ed Tanner online that I'll raise.
I just wanted to share my thoughts. I think the research on cyclones, hurricane, typhoon, whatever we call them, one of the issues is that the research has been very compartmented between geographic areas because those disturbances have different names. For instance, it's not the case for fires because fires is called fire everywhere, but cyclone we have lots. It's the very regional studies, so people only, studies hurricane in the Atlantic, typhoon in the Asia, and cyclone in the South Hemisphere. So it has been very compartmented, and I think we have a lot to learn to try to cross our knowledge between different areas, especially from area where cyclones are very frequent. We have a lot of learned from those areas to transfer this knowledge to area where the cyclones are less frequent or will be more frequent in the future. And also the compartmentation between the different disciplines. So I think in tropical forest ecology, we use functional proxy to analyze the response of forest. And we can see how foresters, for instance, Kana and Thierry, use more process-based traits. So I think we have a lot to learn from that for researching forest.
Thanks. There is a question, as I mentioned, from Etienne, a general question. What are we not recording in fieldwork that we ought to record? For example, will drone data about canopies be useful? I write as someone who does fieldwork and is planning more in Jamaica. I'm not a modeler, but I think that's a really good question. And I know together with Tom, we've been looking at literature and what has been recorded. And if we compare that to what Thierry and Kana talked about in terms of mechanistics of trees, canopy structure, joint canopy structure potentially. So we may not be recording key variables. Any thoughts on that?
Yeah, I think now with LiDARs, we can get a lot of very interesting data on the structure of trees and forests and how the different trees are affected by winds. So doing recurrent surveys before, after, having permanent plots with recurrent surveys, we can have a better understanding of how the structure of trees and forests affect the damages and resilience. So.
Maybe I can follow up with a comment.
Yes.
So, the excellent presentation on agroforestry and the discussion here. I'm just wondering, maybe, we can extend not only our interest in understanding the resilient species, agroforestry species, but I think there's a important aspect of urban planning that needs to take this into account as well. I know places like Australia are looking into it, like Townsville, for example, but in the Pacific Islands, for example, I doubt that they're using any type of cyclone related resistance or resilience into their urban planning.
Yes, and I think that's partially due, that there are more essential questions in a lot of Pacific countries because that's where you get tropical 5 cyclones onto places where buildings aren't necessarily up to standard for tropical, not everywhere for tropical 5 cyclone, and so it's more focused on the protection of life there at the moment, I think, rather than trees. Having said that, better adapted trees might save lives.
That's what I'm talking about. A lot of the places that I worked in use, non-native species, for example, right? So the idea that they will plant native species, not just agroforestry, but outside agroforestry might be something to consider as well.
Sorry, there's a lot of hands up. Swen, then Thierry, and then Eduardo.
Thank you. I was the last raising my hand, but
Oh, sorry,
but
because I
it's
had a
really
comment from you before that I haven't gotten to yet.
No problem. It's related to what you said. But I think that's in tropical islands, one of the issues is also that vulnerability to tropical cyclones is not easy to assess because it's really sparse in location, and so it's difficult to have an idea of how tropical cyclones can reach a given area in category 4 or 5, and what will be the impact, because we have few records actually and few tropical cyclones hitting some places, and so we need for that studies capable of assessing the risk associated to tropical cyclones. And for that, it was something that I presented that is kind of used now, which is this synthetic tracks of tropical cyclones that are constructed from existing database, but to be able to give return periods of events, for example, what can be a tropical cyclone category 5 every 100 years or every 1,000 years in a given place. And we need more studies locally because it's a lot of work to do that. So in each region, to be able to then draw policies relevant for protection and the way we can build a forestry or other stuff.
Thank you. And that's something we've been discussing in very different contexts in our MAK'IT team here, that the importance of having regional relevant policies and regional relevant understanding. So that's a really good point. Thierry, you had your hand up, and then
yes, I'd like to come back to your previous question about what traits you have to measure or we are that has been forgotten in the past, and also to answer Ghislaine's question on the chat. I had mentioned that in my talk and in my answer to Ghislaine that there is a major aspect that is never considered. This is the organization of the branching, the architecture of the crown and on the root system is for me the most important point. It's even more important than the wood density or whatever. This is very, very important. There is a lot of evidence of this, but the problem is that we are not able to, to summarize the crown architecture in a very simple, scalar or trait. This is something very difficult, but I think this is very challenging, and I'm quite sure that we should maybe invest a little bit more on this to find what are the main architectural traits that can be highly correlated with the ability of trees to resist. When strong winds doesn't mean anything, because if the wind is 200 kilometers, the speed is very high. Anyway, the trees will be broken. But you have to. We have to maybe consider this particular question. And AMAP is a good place to do this, I guess, but it's just a comment.
Yes, thank you very much for that, Thierry. And that'll, for our panelists, that'll also relate to our workshop the post-webinar workshop that'll now be in early June, to give us a bit more time to prepare for that. And I'll be in contact about the possible times and dates for that. Eduardo.
Yeah, I just wanted to make a comment about something that really strikes me in this case of the trees on farms and the hurricanes. And this is the divorce between what farmers think and what the foresters think in terms of timber growth. When you ask a forester to come to this farm in Jamaica or in Haiti, and you have these timber trees like a mahogany tree or a cedrela odorata, highly valuable timber species, and farmers in this particular area, one thing they do is they cut the ground completely. And when you ask them why they do that, they always point to me at the distribution of the sizes of the branches. He said, Eduardo, if you look at this tree, a large fraction of the total biomass of the tree goes into branches of sizes that are not really marketable. Only maybe as firewood, but this is obviously a much less valuable product than timber. So he said to me that, okay, if you have all this big crown and all these branches that making maybe 30–40% of the total wood volume of the tree, it's not valuable to them. So what they would like to do is to concentrate the growth into the timber, which is the main stem. So many farmers will go and take a look at the stem and say, well, I can take, let's say, a 5-meter log out of this tree, and they go 1 meter above this 5-meter limit that they're looking for, and then they cut the crown down. Forester will say this is crazy. Farmers say it makes a lot of sense because they come to this tree every 4 or 5 years and do the same. In terms of the supporting structure and the leaf area of the tree, it's not such a bad idea, because if you let the tree grow to develop the crown, you will have a fixed amount of leaf area and a lot of supporting structure for this particular leaf area. If you cut the tree every 4 or 5 years, what you really try to maximize is the relationship between leaf area and the amount of biomass which is supporting the structure. And this is a higher ratio when you prune it. You have more leaf area for supporting the structure. So what really happens is that all the photosynthesis in this leaf area really goes only to one place, which is the main stem. So you can see that the trees really grow fast. The main stem, this 5-meter log they're targeting for, really grows fast. And also there's more cylindrical. So there's not so much taper. So the yield, the lumber yield is really high. So there are a lot of compensatory effects there that really always bring to my mind this conflict between what the farmers do, the socioeconomics behind the management of this tree for timber, and what the forestry science will see. And I think we need more information about that. It has to be the physiologist targeting this balance between supporting and leaf area. How often should this pruning cycle be in order to maximize, the growth of the timber in the main stem and so on? There's so many things that we don't know that I think would be really interesting to see in the future.
Thank you, Eduardo. I think that's a really good point now for Kana, because she's got her hand up, and having just talked about agroforestry and forestry.
I just have a very short comment, because risk management is very important to get the good estimation. And one of my question is, so I said the typhoon or tropical cyclone migrate further north. So the many forests without any experience with a strong wind may be damaged in the future. And I know that Swen said it's very challenging to estimate like a cyclone or the typhoon characteristics in the future. But I'm working on the different projects, how much forest would be damaged in the future because of the changing of tropical cyclones. So maybe the package, the Thomas package would be helpful to, I don't know, to predict something for the future. Or of course, Thierry gave us some very basic, very fundamental theories to how the tree responds. So I don't know, but it's very important and very interesting to integrate the many kinds of knowledge and the ideas they put together to predict the future in the forestry and also in agroforestry. That, yeah, I don't have any solution, but could be interesting.
Yes, thank you very much for that, Kana. And we were really hoping, I think, all of us panelists, that the research into cyclones and how they will change in the future and the impact they're having and how we can better adapt to cyclone impact. We hope that will accelerate in the future, and I'm hoping also that in some way this webinar may have contributed towards moving into that direction. And yeah, so I'm once more very grateful to all of the panelists for giving their time and then discussing further about cyclones and the impact they're having on trees, be it in forestry, agroforestry, natural forests, and as you as Ted rightly mentioned, also in urban environments, which we did not represent here, but which is of course a very big part where trees play a very important role. So yeah, thank you again for your time. Is there anything else? Is there any other question? And I forgot one thing. So Swen also made a comment, and Eduardo sort of mentioned it in passing as well, about using local knowledge, the importance of that, and harnessing that more and integrating that more, and probably testing that more with scientific data would also be a very important future direction. Are there any other questions? Because we're sort of 5 minutes over time, so we managed to stick quite well to the time frame, I think. If not, I'd like to say thank you very much again to all of you. With the attendees, thank you very much for giving your time, and also thank you very much again to the panelists, very much appreciated. And yes, so the recordings will be available soon on my webpage, on my MAK'IT webpage. Sarah already posted the link in the chat, and I will follow up with that to all the panelists. If any of the attendees are not sure about that link, please drop me an email and I will send that to you. Okay, so thank you very much. And
thank you, everybody.
Thank you.
Thank you.
Thank you.
Very good.
Thank you.
Bye.